So till now we have seen many different features on low dimensionality spaces, right? So we started our analysis on how different parameters, or whether it is statistical parameters, we tried so probability, statistics, and all that stuff in dimensions close to 2D, 3D, right? So we always tried analyzing the features or the concepts in 1D, 2D, and 3D. So now today we are going to see how the similar data looks in higher dimensions, right? So that is what our today's deal is all about. So we will see how the data looks like in higher dimensions and what properties are valid, and how it is completely contradicting lower dimensionality spaces is what we will learn today. So technically, it is like not an easy thing to digest the results that we see today in higher dimensions. But considering the mathematical facts and derivations that are coming up, or that we are deriving today, will help us and will make us agree whatever statements that we do made on higher dimensions today. So before starting the session today, I'll just try to revise what a dimension is. So we have seen a data matrix. In data matrix, every row is called as a point, and every column is called as dimensions, right? If we take a particular data matrix related to the purchases made by a person. Okay, so the rows would be each person, like person one, person two, person three, something of that sort, and the columns would be the items that he has bought, like apple, orange, it can be like chocolates, milk, butter, or whatever it is. So all that stuff go into dimensions. So dimensions can be n number, but so when we have huge number of such dimensions, we call that as higher dimensional data. Let's suppose that is what higher dimension is. We have seen this, right? So what we have seen so far, we have seen a data matrix, and the data matrix rows will be called as the points, right? The data matrix rows are called as points. This is called as points, and the column is called as these are called as dimensions. Every column in the data set is called as dimensions. So the dimensions are not restricted based on your data. It can be n number of dimensions. It can be infinite number of dimensions, or fewer dimensions. So we have seen up to 3 dimensions so far, right? We started so much stuff, and we learned so much of stuff, and we analyzed everything. We were able to visualize the data up to 3 dimensions, and when we have gone to 4 dimensions, it had become little tough for us. So it is technically, when we just come to 4 dimensions, it is really difficult to actually go ahead and visualize that data in 4 dimensions. Okay, so look at this. We are just we started, and we are just trying to understand the data in 3 dimensions, and we were able to visualize successfully up to 3 dimensions. When we go to 4th dimension, what happened is the geometrical visualization will really become very complex. It is I would say it is very difficult to visualize just when we go to 4th dimensions, and when the dimensions reaches infinity, it is near impossible. It's I would say it's impossible to visualize the data in geometrical uh, representation. So then the only possible way is to do the mathematics around that data, around those dimensions. Okay, so just for your reference, I would just show you how an sphere looks like in 4th dimension. So this is how a sphere looks like in 4th dimension. So it is little bit looking like complex stuff, right? So this is just at 4th dimension, the diagram is making so much complex appearance. So as we increase the dimensions to infinity, at least up to 10D, you can just imagine it is really very difficult to visualize the data. So to visualize the data in higher dimensions, the only thing that we do is always do the mathematical interpretation around the um, dimension. So how we do all that stuff, and what statements that we can draw through that mathematical analysis is what we are going to study now. So our whole purpose of this session today is to understand the different concepts in higher dimensions. It can be calculating the distance between 2 points in higher dimensions, or finding out the similarity between two data points in higher dimensions. So how does the Euclidean distance look like in higher dimensions, and how does Mahabolonius distance looks like in higher dimensions is all what we are going to study today. Okay, so let's, with that in place, like just start understanding what higher dimensions is. Higher dimension space is one where the number of dimensions, we also call this as futures, right? So we have seen futures and label. Can someone say me the difference between what is a future and what is a label? Difference between a future and a label.
Features are referred to as input and label is referred to as output.
Yeah, so label is the derived variable from the features. Features will be fed as an input to the model. So that is the difference between the feature and a model. So higher dimension space is one where the number of dimensions or features is very large. So when these dimensions are very large, we call them as higher dimensions. So as we all discussed, it is very difficult to visualize the data geometrically. It is very difficult to visualize the data in geometrical space. We just have seen an example of 4D and it looks like very complex thing. So when we just go to 5D, we just need to drag that to another space. I mean, we just need to drag the same diagram and we have to join all the points. So it actually, the baseline is, it is typically impossible to view the data in higher dimensions or visualize the data geometrically in higher dimensions, I would say. So I'll just take an example of, the data, an example of data in higher dimensions. And this is a real world example. So you could easily understood this. So the main criteria here is that you have two textbooks with you. Okay. So you have, or I would say two documents with you, two big documents, or PDF documents of 100 pages and 100 pages. Are You have such a huge documents with you. Now you want to compare whether these two documents are conveying the same information or not. Let's suppose you can take any book. Let's suppose if you take machine learning books, uh, these books will be written by different authors. It can be author one, and it can be author two, or whoever it is. So, but they both try to convey which subject both the books written by authors will try to convey machine learning concepts. Okay. Now you would say these two books that you have, even though the content, the wording is different, are different in both the books, but they both will try to convey the machine learning language, or the machine learning subject to the readers, right? So now you are given such a kind of documents, and you were asked to find out the similarity between both the documents. When you say similarity, what does similarity means? Whether both the books are conveying the same subject or not is what you have to find out. Let's suppose one document is telling about machine learning and the other document is talking about Telugu literature. Okay, so if the other book is talking about Telugu literature, yeah, when you are asked to find out the similarity between these two documents, you would say they are not similar at all. When you say the same subject is written by two authors, you should be able to say those two documents are similar to each other because they both are trying to convey the same subject, right? Now, such a kind of comparison is a good example for this. And how do we actually compare the similarity between two documents when such a huge document is given to you is what we are going to find out now. Okay, so let's read this and go back to the explanation of the same. So what is this saying now? Document comparison in natural language processing. Okay, let's leave about this natural language processing. So we are all doing about document comparison. We haven't gone to this stage yet. We will go there at some point of time. But right now we are just trying to understand what is document comparison, and how we are going to do it with a simple example is what we're going to see now. Suppose you have a collection of text documents and represent each document as a vector in higher dimension space. Okay, so as I told you, each point can be a vector, right? We can represent this as a vector. How do we represent this as a vector? If you take each column as a dimension. Dimension can be I, J, K, or whatever it is. Here the dimensions are apple, orange, banana, grape, and pear. So we call these as dimensions, right? So we can represent this point in dimensional space. How can we represent this point in dimensional space? It is just like I of apple, I of j, or we can, if it is in vectorial form, we can just represent it this way. 1, 1, 0, 0 is one of the vectors, right? So suppose you have a collection of text documents and represent each document as a vector in higher dimension space. Okay, the dimensionality corresponds to the number of unique words in the vocabulary where each word is a feature. Understand this. The dimensionality corresponds to the number of unique words in the library. So how we do the comparison between two documents is you go through the entire document, read the entire document, and fetch out the unique words. Okay, so and make a matrix with that particular unique words. And then once you count the number of words in each document under a specific word, once you get that information, you would just do the similarity matrix, or you can just find out the cosine similarity between these two things. When I say cosine similarity, what does that mean? You find out cos theta between 2 points, right? Right? What does that actually said to you? When you try to find out cos theta between 2 points, if it is equal to, if theta is equal to 0, and if theta is equal to 90, when theta is equal to 90, what is the value of cos theta? It is equal to 1, right? When cos theta is equal to 0, what is the value of it? Sorry, it is 0, right? Cos 90 is 0, cos 0 is 1. So what does this specify? When angle between 2 points is 0, that specifies they both are similar, right? They both are going in the same direction. When the angle between them is 90 degrees, those 2 points are far from each other and they are not similar to each other. That is what we have studied, right? So we call that as cosine similarity calculation. Such a way you can find out the angle between these 2 points, and based on the value that you have got, you can say whether they are similar or not. Okay. We have done this part, right? Calculating the cos theta and find out whether whether 2 points are close to each other or not. And if both are close to each other, we said like they are similar or not similar. I think you already have done an question on the same in the assignments that I have shared. Is that right?
Yes.
Right. So it's as simple as that. Now let's leave about the complex documents that we were talking about, which can have thousands or I would say 10,000 words, different unique words, and you don't want to consider like when you have 10,000 unique words, you can say that as higher dimension space because you have 10,000 such kind of rows extended for every point. Okay, so that is called as higher dimension space. Just to understand how do we actually compare, you can take this as a complex document with 10,000 words, but to simplify the concept, I'm just taking 3 words here in the first document and 2 words here in the second document. Now, what are we going to do is we are just trying to find out the number of dimensions found by these two documents. So to find out the dimensions, when you are doing the document comparison, what we do is you will get the unique words in both the documents, right? What are the unique words in these two documents? So apple is a unique word, orange is a unique word. So this is done. Orange is a unique word. So these two are done. Banana is a unique word. So these two are done, right? So these are the unique words. You have framed all of them: apple, orange, banana. Let's suppose you also have grape in the first document and pear in the second document. I would say grape is also there in the first document. Um, pear is also there in the first document. Or else you can just ignore that. Like, let's say I have, a grape and pear in the first document. Or you can also say, I would take it this way to just match the documents. Okay, let's say I would take a third document and I would say that document has, two other fruits. So I have document of 3, and this document has grape and pear. Okay, this has grape and pear. So these two are there in my third document, right? So now if the unique words in all my documents is apple, orange, banana, apple, orange, banana, grape, and pear. So I have, with my unique words, I will form 5 dimensions. Okay. And how many documents I have? 3 documents, document 1, document 2, and I would also say document 3. So now in document, you have one apple, right? So this count will become 1. You have one orange, right? So the count will become 1. Banana one time. So you will have 1. So if you have apple, orange, banana, banana in the first document, then what you will get? Banana as 2 is what you will get. Okay. So it is, this number is just the count of the word in that particular document. The number of times a particular word happened, the unique word happened in the document is just this count. So number of times grape appeared in document 1 is 0, pear is 0. When you go to the document 2, apple is 0, orange is 1, banana is 1, grape is 0, and pear is 0. Now can you say me what would be my vector for document 3?
0, 0, 0, 1, 1.
Okay, so it is 0, 0, 0, 1, and 1 would be my vector for document 3. Right? So because you don't have apple, so the count would be 0. You don't have orange, so the count would be 0. Banana, 0. But you have grape and pear, so the count of them is 1 and 1. Now if you want to find out whether these two documents are similar or not, or they are talking about the same subject or not, you can just find out that using finding the angle between those two things, cos theta. Cos theta is nothing but dot product of those 2 points by modulus of those 2 points. So what is the dot product between these two things? It is 2, right? Because 1 dot 0 is 0, 1 dot 1 is 1, 1 dot 1 is 1, 0 dot 0 is 0, 0 dot 0 is 0. So you have 2 here. Dot product is 2, and what is the modulus of a? Modulus of a is root 3 into root 2, right? So this becomes root 2 by 3. So what is the angle in that case? So root 3 by, so you have theta is equal to 90. Cos value ranges from 0 to 1. So it is falling somewhere between root 2 by 3. What would be the value of it?
0.8.
0.
86.
0.86, right? So what does that says? So it is close to 1. So those two documents are similar is what you can say, right? So now if you calculate the similarity between these two documents, what is the cos theta for these two? It is 0, right? Cos theta is equal to 0 because 1 dot 0 is 0, 1 dot 0 is 0, 1 dot 0 is 0, 0 dot 1 is 0, 0 dot 1 is 0. So cos theta is equal to 0. So when you say 0, those two documents are not similar because the angle between them is 0. I mean, angle between them is 90. When the angle between them is 90, they are not similar at all. So document 1 and 2 are similar to each other, and document 1 and 3 are not similar to each other. So there is no, they are talking about different subjects is what you can say. So these two documents are not similar. They are talking about different subjects. And document 1 and 2 are similar to each other because you got the cos theta as root 3 by 3. So it is close to 1. So that means, they are similar to each other. So these two documents are similar to each other, and you can say both are talking about same subject. So this is just a simple example of looking at higher dimensional data or constructing a higher dimensional data comparing two huge documents or two documents is what you can say is an example of creating is an example of higher dimensional data. Now you were able to calculate the cosine similarity as the dimensions was close to 5. And now when you have higher dimensions, like when you have 10,000, 20,000, or infinite number of dimensions, you will find out whether you are able to calculate this similarity, cosine similarity, whether you are able to apply cosine similarity or not for those points, whether the same concepts that we have learned, the distance between two, two points, whether it is Mahalanobis distance. What does Mahalanobis distance says? When a given point is close to the mean of the distribution, we can say that is part of the distribution. If it is far from the distribution, Mahalanobis distance will give a larger value, which specifies that it is not part of the distribution, right? So whether the same can be applied in higher dimensions or not is what we are going to learn. Okay. So this would be very interesting because whatever we have studied in 2D, I'm just revealing, like, whatever we have studied in 2D will not applicable in higher dimensions. Why we cannot apply the same cosine similarity formula to find out the similarity between 2 points, or why can't we use Mahalanobis distance or Euclidean distance in higher dimensions is what we are going to study. So it looks little interesting, and as you go through them, you will not able to digest them. The reason being, you cannot accept them. They look like unacceptable, but the mathematics shows us they're true in that higher dimension space. So whatever we have studied so far, like cosine similarity, Euclidean distance, won't apply for higher dimensions. So that is what we are going to learn today, and why they are not applicable in higher dimensions is what we will learn using the pure mathematics, because geometrical interpretation is not possible in higher dimensions. Okay, so going back to the next slide, we are just trying to understand hypercube. Okay, we all know what a cube is. Cube, the best example of cube is just our room in which we are sitting right now. So this room, the room around you is an example of a cube. So it has 3 dimensions and it's a closed box. Okay, so hypercube in 1 dimension is a line. Okay, so it all starts with a point in 0th dimension. When you say 0D, okay, when you say 0D, it is just a point. A point is a 0-dimensional hypercube. And when you say 1D, you have to extend the 0D in the next dimension, okay, into one of the dimensions. You have to drag that point to one of the dimensions. That is all about extending from one dimensions to other dimensions. We already have studied this, but I'm just repeating. So when you say 1D, it just means that you have this green point. You have to drag this point along the other dimension. Okay, let's suppose I have this x-axis. I have to drag this point along x-axis. Okay, so that becomes 1D because I have dragged this point or expanded this point along one of the axes. So that becomes 1D. So this is 1D. 1D hypercube is a line. Now what I have to do, I have to extend this along other dimension. So now I extended this along x-axis. If I extend this point, the same line along y-axis, what I just have to do, I just have to drag this point. Okay, I just have to drag this point along the other axis. I would drag this along y-axis. So what I'll do, I'll just drag this along y-axis. So this becomes, when I drag this, this goes and forms a square, right? So these are all of equal lengths and this forms a square. What I have done, I have dragged this line along y-axis. Okay, it forms a square. Your floor is an example of the square. Now what I'm going to do, I'm going to drag this square. So in 2D, hypercube is a square. Now I'm going to drag this floor towards the other dimension, which is z-axis. So we are lifting this, we are just lifting this box along z-axis. So what we are going to do, we are dragging this along x-axis to form a room, right? This is a room and these are the walls of the room. So when you lifted this or drag this 2D along the z-axis, this is the z-axis. So if you drag this along the other axis, which is z-axis, it forms a cube, right? Look at this. So this is the square, right? This is square. The bottom is the square. Now what we are doing, we are lifting that along z-axis. When you lift this along, when you lift that floor towards the z-axis, which is your border of your room. Okay, so when you extend that along the border of your room, you will get a 3D. So this is the cube. And if you drag this along the other dimension, okay, look at this. This is a cube. Just concentrate on this. This is looking like a cube, right? So it is the floor, it is your slab, and these are your walls. Okay, so these are your four walls. So this is a room kind of stuff. This is a 3D cube. To go to 4D, what you have done, you took a copy of this. This is a copy of this. Okay, so other part, this one that you're seeing is just a copy of this one. So this is a copy of this one, and then you're joining all the vertices of both the cubes to form a 4D. Understood? So the only thing that we're doing to go to the higher dimensions is take that point, drag in other direction. Take that point, take that line, drag in other direction to form this. And take this 2D and drag towards z-axis to form a 3D. And take 3D and drag it along other axis or other dimension to get the 4D. And 5D is same as that. Look at this. So this is taken. So this is 4D and this is 4D. Take a copy of 4D and join all the vertices to form 5D. Okay. So this is how the dimensions will keep on growing. Look at this. Just visualizing the 5D is becoming difficult for Hypercube. When you go to 60, take this whole copy again and take another copy of this, join all the vertices to form 60. Okay. That is how the dimensions will keep on extending. Understood? How does a hypercube looks like? Hypercube is a generalization of cube in higher dimensions. Hypercube is nothing but a cube in higher dimensions is called as hypercube. So unit hypercube will have a length of 1 in each dimension. What does that mean? Length of 1 in each dimension means each side will have length 1. Okay. So each side of the cube will have length 1. So this has length 1, this has length 1, and the height is also length 1. So that is how a hypercube actually unit hypercube actually looks like. So the difference between hypercube and a unit hypercube is that unit hypercube will have a dimension of 1. Okay, that is all what it actually means is. That is what a hypercube basically means. Is this clear?
Yeah.
Okay. So just for you to visualize, this is how a hypercube looks like in higher dimensions. So look at this. It keeps on extending, right? So a cube, this is a cube. Okay, this is the upper cube. And look at this. This is another cube. Let me take a different color. Okay. So this is one of the cubes, right? Look at this. This is forming one cube. And this one, this is the red. This is another cube. We are joining both the joints. Look at this. You're joining all the edges. So the hypercube actually looks like this, a lot of ladder kind of stuff. Okay. So just for you to visualize, you can just look at this for a few seconds and just what we have studied is what you have to analyze here. Okay. So what we have studied, we have taken a point, extended that along z-axis, right? So we have extended that point along that axis. We have taken a point, extended that along one of the axis, and then this line is extended towards this axis, and then this plane altogether is extended along this axis, so which formed a cube, right? This formed a cube, and now we are stretching this cube. We are moving this cube towards this direction. Okay, towards the direction. Look at this. There are many cubes here. There are many cube. This is forming a cube. Look at this. This is a cube, right? So joining the vertices. of both the cubes will form the hypercube in higher dimension. So we are seeing so many cubes just because we are just taking and moving to the next dimension and joining the vertices. That's why you are looking at so many squares or cubes kind of stuff in this diagram. So that is how you have to visualize this. Hypercube is nothing but a cube in higher dimensions. You can just have a look at this to look at how the diagrams look like in higher dimensions. Just try to visualize the concept that we have learned before. So just make sure the diagram is just extending to the other side and the vertices are being joined is what you have to understand in this. Okay, so this is the best example of an hypercube in higher dimensions. This is how a hypercube looks like in higher dimensions. Okay, and then going back to the next screen. So hyper rectangle. So you today you have to understand what is what is hyper rectangle. Hyper rectangle is nothing but a rectangle extended to other dimensions, right? Now we have seen a square extending to the other dimension. The rectangle is that you will not see the equal lengths on all the sides. You will only see the opposite sides equal. So when you extend that rectangle to the other dimensions, it will just forms the hyper rectangle. So that is all what this is all about. Okay. You're going to just extend a rectangle to the higher dimensions. Like let's suppose if you are moving to the 3D, so these two sides are all the sides are not equal, only the opposite sides are equal. Okay, I mean in this case whether it would be opposite faces or whatever it is, and you take the same rectangle and go to 4D. So take the same um, hyper cube, hyper rectangle, and then join all the faces. So that's how you form a 4D hyper rectangle. Okay. So rectangle is just nothing but hyper rectangle is not just nothing but generalization of a rectangle to higher dimensions. A rectangle in higher dimensions, unequal lengths in each dimension. That is what it is. So just look at it. It's like unequal dimensions in all, unequal length in all dimensions is what you have to understand. Okay. It is just an unequal length in all dimensions. It's not just opposite directions. In 2D you will see the opposite directions are equal, but you will have it, if you have a third dimension, the third dimension will have a different length to the first dimension and the second dimension. So that is what actually it is. Okay. Mm. Just look at this, like you have one dimension which has specific length, and when you go back to the second dimension will have length different to the first dimension. This is 1D. This is 2D. And in the second dimension, you will have a different length. When you go to the third dimension, it has a different length. Third dimension will have a different length. Something like this. So first dimension is different. Second dimension is different. And third dimension is also different. Okay. So this is the third dimension. The length of the third dimension is different from 1D, 2D. So this length is little large. So that is how an um, rectangle, what do you say? Hyper rectangle looks like. So when you say fourth dimension, it can go just beyond this. This length would be, this 4D will have a different length. So this is where it can form another rectangle, something of this sort. Okay. So it forms a similar diagram to be pasted here, something like this. And then this extends, the same diagram actually extends. So the both will be joined. Okay. So this actually goes here as well, but they will be joined by different vertices. So that forms an hyper rectangle. But what you have, that is what unequal lengths in each dimension means. Okay. When we normalize hyper rectangle, we will get a hypercube. What is normalization? What is standardization? We have studied about standardization, right? standardization, Z score. You remember that? We were able to convert every normal distribution to standard distribution. Standard distribution will have mean of 0 and standard deviation of 1. And I explained that process as standardization, where any kind of normal distribution is converted to standard deviation. And using that Z distribution table, we were able to find out the area between any 2 points. And then the same area applies to the actual normal distribution as well. Anyone remember that? Okay, so normalization is such a kind of stuff, scaling or transforming the dimensions of a particular figure. Okay, so here what we are doing, normalization is scaling the dimensions of a hyperrectangle such that each dimension ranges from 0 to 1. So when we normalize a hyperrectangle, we will get a hypercube. Okay, so that is what normalization actually means. Normalization means scaling the dimensions of a particular figure. Now, how do we perform this normalization? So one kind of normalization is min-max normalization. So how do we normalize using this particular formula? So look at this. If I normalize this, what happens is, to which diagram this is converting. Now I'm trying to normalize this particular diagram. I have 4 points, 0, 0, 5, 0, 5, 2, and 0, 2. Okay. So now if I normalize these things, which diagram I'll get is what I'll see. What this statement is saying, when we normalize hyperrectangle, we will get hypercube. Hypercube means all the sides has to be equal, right? That is what hypercube means. So what this statement says, when we normalize hyperrectangle, this is hyperrectangle because the length is not equal on both the sides. Here the length is 5, here the length is 2. The lengths are not equal. So this is hyperrectangle. When we normalize this hyperrectangle, it is saying like we will get a hypercube. Okay. So let's see if you're getting hypercube or not. Hypercube is nothing but all the sides are equal. So normalization, now where they are saying normalize. What is normalize? Normalization is scaling the dimensions of the hyperrectangle. In fact, any diagram. Okay. It can be rectangle or whatever it is, pyramid or whatever it is. Scaling is nothing but normalization is nothing but scaling the dimensions. So the dimensions ranges falls from 0 to 1. So all the dimensions will be brought to 0 to 1. Okay. Now how to do that normalization is just use this formula. Nu x is equal to xi minus min by max minus min. What is this min and what is this max? We already know xi. We want to find xi bar, which is the normalized dimension. Okay. We know x is xi in every case. So this is here the xi is 0, here the xi is 5, here the xi is 5, and here the xi is 0. So this is xi, and this point on the other side is yi. Okay. Now if you take all the xi points 0, 5, 5, 2, 5, 0. So we have 0, 0, 5, and 5. So what is the minimum value in this range? Minimum is 0, maximum is 5. This is for x. And now if you go back to y, what are the minimum and maximum values of y? So if you go back to y, what are the minimum and maximum values of y? So the minimum, what are the y's here? 0, 0, 2, and 2 are the y's, right? Y's values are 0, 0, 2, and 2. So the minimum value of y is 0, the maximum value of y is 2. So this is min, and this is max. And this is min, and this is max of xi. Now let's convert this point 0, 0, and let's see what we are going to get. So I'm applying this particular formula. So xi minus minimum of I is 0, of x it is 0. What is maximum? Maximum is 5, and minimum is 0. Okay, so that is xi. Yi, now I have to find out yi bar, transformed or normalized yi point. Okay, that is yi bar. To calculate yi bar, I just have to replicate the same formula. Xi changes to yi now. So yi is 0, minus minimum of yi is 0 by maximum of yi is 2 and minimum is 0. So this becomes 0 comma 0. Okay, so that became 0 comma 0. Now let's try to convert 5 comma 0 now. Okay, what I'm going to do it try now, I'm going to try to normalize. uh, now I'm going to try to normalize 5 comma 0. So how does this change is what we are interested now. Let's try to normalize this. So to normalize this, the same formula, xi minus minimum of xi is 0 by maximum of xi is 5 minus minimum of xi is 0, comma, what is yi here? 0 minus minimum of yi is 0 by maximum of yi is 2 minus minimum of yi is 0. Okay, just use this formula, replace xi or yi with these points. Minimum comes from this, maximum comes from this for x. Minimum of y comes from this and maximum comes from this. So what is this point coming down to? 5 by 5 is 1 comma 0. So when we normalize, this point changed to 1 comma 0. This is normalized point. 0 comma 0 remained as 0 comma 0. Now look at this. It started converging to hypercube. So this side is 1 now. Now let's try to find out this particular point. 5 comma 2. Just apply the same formula. 5 comma 2. If you want to normalize this, this becomes 5 minus 0 because xi minimum is 0 by maximum is 5 minus 0, comma, what is y here? 2. 2 minus minimum of y is 0 by maximum of y is 2 minus minimum of y is 0. So this became 5 by 5 comma 2 by 2. So which is, sorry, 5 by 5 comma 2 by 2. So which became 1 comma 1. So this became 1 comma 0. This became 1 comma 1. What is the distance between these 2 points now? It is 1. Okay. Similarly, if you change this, this becomes 0 comma 1. Okay, so now what happened? The hyper rectangle changed to hypercube. Look at this, all the sides will have equal lengths or a length of 1, which means it is a square. So that is what normalization means. When we normalize a hyper rectangle, we will get a hypercube. Okay, so that is the relation between hypercube and hyper rectangle. Hyperrectangle is nothing but a rectangle in higher dimensions. So rectangle will always have unequal lengths, right? Unequal opposite sides. When we go to third dimension, the third dimension length will be different from first dimension and second dimension. When we go to fourth dimension length will be different from 1, 2, and 3D. Okay. So that is all about hyperrectangle. Is this clear?
Yes.
Okay. And going back to the next slide. Hypercubes. We covered this as well. Right. Now we talked about hypercube. You understood what a hypercube is. You understood what a hyper rectangle is. And you also understood what is normalization. And you also understood how to convert what happens when a hyperrectangle is normalized. Right? What happens if hyperrectangle is normalized?
It converts to Hypercube.
Yeah, that converts to hypercube. Right? Now let's try to understand what is hypersphere. Okay, hypersphere is defined as set of all points in n-dimensional Euclidean space that are at constant distance from the center point. Okay, a hypersphere is a higher dimensional analog of sphere. Hypersphere is nothing but a sphere in higher dimensions. Okay, so now let's understand the first statement. A hypersphere is defined as set of all points in set of points. Okay, what is this set of points? these points are at constant distance from the center point. Let's suppose if you take this point as a center point, all the points which are at equal distances. Okay, this is my center point. All the points which are at equal distances. So this is R. So this can be a point with radius R at a distance R, I would say. All these points which are at equal distance from the center point forms a sphere or hypersphere or whatever it is. So look at this. This is all forming a circle, right? So we are just talking about points only at equal distance from the center, not all the points. Okay, we are just talking about the points. Point here, point here, point here, point here, point here, point here. So we are not talking about points which are there here. So these points will not form a hypersphere or sphere at all. So these points are not part of sphere. Only the points which are at only the points which are at equal distance from the center, okay, are called as are will form a hypersphere. Okay, so that is what actually it means is now by now you should be able to understand only these points on the which are at equal distance from the center will form a sphere. Now anything which is inside this or any point which is beyond R or less than R will not be part of sphere. A sphere is defined as set of all points in an Euclidean space. These are all Euclidean spaces that are at constant distance from the central point. What is that constant distance called? That constant distance is called as radius. A hypersphere is a high dimensional analog of a sphere. Okay. If R is equal to 1, if radius R is equal to 1, we call that as unit hypersphere. Okay. If R is equal to 1, we call that as unit hypersphere. I mean, if the radius is 1, we call that as unit hypersphere. When the length of the side is equal to 1, we call that as you know, hypercube. Okay, that is what hypersphere is. Now let's look at hypersphere in different dimensions. Again, when it comes to zeroth dimension, when it comes to zero dimension, it is just a point. When it comes to 1D, it is just one point at that, at that distance at R. So it forms a line. When it comes to 2D, all the points at equal distance from the radius. That means, it forms a circle like what we have seen here. It forms a circle. So in one dimension, it is radius. And if it is a two dimension, it forms a circle. Okay. This is a circle. And when you go to three dimension, it forms a sphere, right? What is sphere? This equal distance from the radius. So if you consider a floor, okay, if you take the floor, that forms what does that form? That forms a circle, right? That forms a circle on the floor. And also if you take a center of that circle, all the points at equal distance, like consider this as a 2D. Okay, this is a circle on the floor. Now every point that is coming forward with radius r will form an sphere. So it is like a ball. Okay, are you able to understand like sphere, right? So every point on this surface will be at distance r from the center. Okay, all such points will form a sphere. It's like a globe. We have seen globe, right? The globe looks like is the globe is a good example of sphere. Every point on that globe will have equal distance from the center, which is equal to r. If that r is equal to 1, we call that as hypersphere. And it's same as like when you go to fourth dimension, every point, if you look at this, so from this center, every point will have on this circle will have, I mean, on this diagram will have equal distance r. So that is how the 4D sphere looks like. Okay. So the base thing that you have to understand is every point which is at distance r from the center will form a sphere, whether it is hypersphere or a circle or a sphere in 3D, or a hypersphere if it is beyond 3D, we call that as hypersphere, and that also will have equal distance from the center, but in the fourth dimension. It is really tough to visualize the fourth dimension, and this is how complex it becomes. So from this to this, it became very complex, and when it goes to 5D, it became much more complex. Understood? So hypersphere is just that. Hypersphere with radius are empty inside. So the points inside this doesn't form hypersphere, just the boundary, because we are bothered about only the points which are at equal distance from the center. Okay. When the radius is one, we call that as unit hypersphere. So that is what hypersphere actually means is. So there is a reason why we are actually trying to understand these diagrams in higher dimensional spaces, because all the derivations that we're going to learn forward will all deal with this cubes and spheres. The reason being, any data set, if you take any data set, that would most probably resemble like a square, right? Like a cube. So in 3D, if you're taking some set of diagrams, like this is the 3D, if you take any set of points in 3D, so you can resemble that as a cube, right? All the points in a cube or in a room. So that is why we are studying about all this. If the points are forming a circle kind of stuff, you can consider that as a sphere, right? If they're forming something like this, like a circle kind of stuff. So the most of the data sets that are there in the real world will inscribe into one of these diagrams. Okay, that is the reason why we are learning about these different diagrams and the properties that are associated with these diagrams. Okay, and the only difference between hyperball and a hypersphere is they both are equal, but hyperball also includes the points within it, within that circle or within that radius r. So hypersphere is bothered only about the points which are at distance r from the center point, but hyperball includes all the points within that space. So the best example is, look at this. Cogball is will have that inner material also combined, right? It is filled. So the inner filled material along with the outside will form an complete ball, right? That is what hyperball actually. This would be a good example of hyperball. And when you take the other example of tennis ball, the inside is void for this. The tennis ball is will have only the outer part, right? So inside is void. If the inside is void and those points are not part of your diagram, that is called as hypersphere. And if you are considering the inner points also, everything inside, not just the boundary, if you're considering everything inside, then we call that as hyperball. That is the only difference between hypersphere and a hyperball. Okay, so now we have studied what is higher dimensions, what is a good example of higher dimensional data set. Like document comparison is a good example where we have n number of unique words in the document. And then we have studied about what is that, hypercube, and we also have studied about hypersphere. We studied about hypercube in 0 dimension, 1 dimension, 2D, 3D, 4D, and we also have understood how does it looks like in higher dimensions. It is just an extension to the other dimension and just join all the vertices. And unit cube is nothing but when side of each cube is equal to 1, we call that as a hypercube. And then we studied about hyperrectangle. Hyperrectangle is nothing but uh, the the dimensions are unequal in each dimension. I mean, unequal lengths in each dimensions. And when we normalize hyperrectangle, we get hypercube. And we also have seen what normalization is. It is just about scaling the diagram. And we have seen min-max normalization. And then we have went to hypersphere. We understood hypersphere in 0D, 1D, 2D, right? And then we understood what a hyperball is and what is the difference between hypersphere and hyperball. So that is where we are right now. And now comes the real stuff that we want to look at. So these are just mathematical representation of a hypercubes. Okay. What does this actually means is, look at this simple analogy behind it. You now know what is a hypercube, right? Hypercube actually looks like this. So if my length of my hypercube is 2, okay. So if my length of hypercube is 2, what does this point look like? Let's say this is 2, this is 2, okay, this is 2, this is 2, and this is 2. And how does my point actually look? How does my points actually look like? If I take this point as origin 0, comma 0, comma 0, if I take this as 0, comma 0, comma 0, if I take this as 0, comma 0, comma 0, and what this length is 1, this length is 1. So let's consider this as x-axis and this as y-axis. And this length is 1. What does this point will become? Let's say 0, comma 0. This is two-dimensional, this is 0, comma 0. And what does this point looks like? It looks like 1, comma 0, right? Right? This point is 1, comma 0. So this point becomes minus 1, comma, right? What does this point will now become? What does this point become? If that is y-axis, that becomes 0, comma minus 1, right? That becomes 0, comma minus.
Minus.
This becomes 0, comma 1. So look at this. Every point is between minus 1 and plus 1 in a hypercube. And it depends on the length of the cube, hypercube as well. If it is 3, it may goes to minus 1.5. So but in general, it's kind of like all the points will always, like in most of the hypercubes, when you normalize it, it all falls between these ranges. Okay, the cube may tilt towards negative axis, so that becomes if the unit cube is minus 1, so if it is residing it may goes to minus 1. If it is completely residing towards the positive side, it may goes to 0 to 1. Okay, so this applies for unit hypercube, but in if we are considering a general hypercube, this may be anything. Okay, so that is what actually this point means. So if you take a two-dimensional point, now we are talking about two dimension. When you are talking about two dimension, you will have 2 points, and these 2 points may just be within minus 1 to 1. Each xi, what are the xi's here? Minus 1 and 1. Each xi may stay in this range between minus 1 to plus 1. And if you take the other x2, so when you are talking about two dimensions, x1 and x2, we call them as x1 and x2 when you're talking about higher dimensions, because you cannot say x, y, z or something like numerical, I mean alphabetical letters for different dimensions, because dimensions will be infinite. You will just have 26 words, and it is usually difficult to assign names to each dimension. That's why we call in higher dimensions, each dimension will be named like this, x1, x2, x3 or something like that. So x1 is one dimension and x2 is other dimension. So when you come to x2, again the points are 0, comma minus 1 and 1. So they are also falling within minus 1 less than or equal to xy is less than or equal to 1. So that is what this mathematical representation of an hypercube actually looks like. Okay. If it is three dimension, how does the three dimension points look like? It looks like something like this, right? 0, comma 0, comma 0, 1, comma 0, comma 0, 0, comma 1, comma 0, 0, comma 0, comma 1, right? This is how the points look like. Even if you look at 3D diagrams, all the x's will lie only between minus 1 and plus 1. Okay, it will not go beyond that. This applies for unit hypercube only. Okay, if the cube is towards the negative axis, right? If it is residing here, like if you take two-dimensional point and this is 0, comma 0, comma 0, and it extended towards the negative axis, then this becomes minus 1, comma 0 in two dimensions, right? It is not going beyond this value. This becomes 0, comma 1, and this becomes 0, comma minus 1. Even if you look at this tilt, so it is staying between minus 1 and 0, right? Minus 1 and plus 1, if it's tilting between these two. So that is the reason minus 1 less than or equal to x is less than or equal to 1. Okay, x is between minus 1 and 0, y is between 0, and the other dimension is between 0, comma 1, minus 1 and 1. The minimum value is minus 1, the maximum value is plus 1. Okay, even if you take the x-axis tilting towards this, then what does this becomes? This becomes 0, comma 0, and this becomes 1, comma 0, and this becomes 0, comma 1, and this becomes 0, comma minus 1. I think we are putting it in a wrong way. This becomes 0 point minus 5, minus 0 0.5, right? This becomes 0 0.5. Is that right? Because the length is 1, the origin is at 0 comma 0, so this becomes 0 0.5, this becomes minus 0 0.5. So even then we are just residing in between minus 1 and plus 1. If it is completely in the upper side of x-axis, if you're taking this way, it becomes 0 comma 0, 1 comma 0. This becomes 0 comma 1. Okay, so this unit cube will have values between minus 1 and plus 1. Okay, so even if you take hypercube in any space, okay, the values will always lies between minus 1 less than or equal to xi is less than or equal to 1. What are the possible ways of putting in hypercube on different sides? It is as simple as this. Just take this as two dimensions, x1 and x2. We can place a hypercube here. This is my first hypercube with length 1 and 1, with length 1, and the other hypercube is it can stay here depending on the stuff, right? This can be one hypercube. This square can lie here, or it can lie here, it can lie here, it can lie here, right? Do we have any other combinations? In these cases it will be 1 and 1. X will be 1, y equal to 1. In these cases x will be 1, y will be minus 1. In this case x will be minus 1, y will be minus 1. In this case x will be minus 1, y will be 1. So if you look at that, it is always between minus 1 and plus 1. The points are always between minus 1 and plus 1. Here there will be 0 0.5 and 0 0.5, plus 0 0.5 to minus 0 0.5, plus 0 0.5 to minus 0 0.5. You just extend this 2D to 3D. In any case, all the values will always be between minus 1 and plus 1. That is the actual representation of this hypercube. Is this clear? The hypercube contains all points where each coordinate lies between minus 1 and plus 1. Is this clear for you? I'll just put forward the other example. I mean, the simple example to show you. Like if I take this cube,
Yes.
what are the points becomes? This becomes 0 comma 0, right? This becomes 1 comma 0, right? This becomes 1 comma 0, and this becomes 0 comma 1. So in both the cases, the value is between minus 1 less than or x and 0 comma 1. This case 0 is less than xi is less than 1, right? If you take the other case, like let's take this example, this diagram, this cube over here. So it is falling here, right? So that means what is this point? This point 1 comma minus 1, y will be 1 comma minus 1. So this becomes 0 comma minus 1, this becomes 1 comma 0, and this becomes 0 comma 0. So the values are lying between minus 1 and plus 1, right? In this case, so if you take any square, any cube or any hypercube, if it is a unit hypercube, this is a mathematical representation. If it is not a hypercube, it can be just like if it is depending on the length of the cube, minus L less than or equal to x, I is less than or equal to length L, which where L is the length of the hypercube. If it is unit hypercube, L is equal to 1. Is that clear? Hello.
Yes, yes. Yeah,
Yes,
it's clear.
Okay. Now we are talking about hypersphere. Okay. I'm erasing all the points here. Now we are talking about hypersphere. Hypersphere, what we have discussed, all the points which are at distance r from the center is defined as hypersphere. So circle is an example of hypersphere where x1 square plus x2 square is equal to r square is the diagram of it. I mean, it's a representation of a circle. This is the representation of a circle, and we are just extending that to higher dimensions. If there are n dimensions, we just extend x1 square plus x2 plus square plus so on xn square to r square. So that becomes the equation for a circle. Okay. That is what it is. So if you want to validate this, it is again simple. So if you want to take the circle at with radius 1, if you take this as dimensions again, if you take a circle of radius 1, everything at radius 1 will be the part of the circle. So this is 1. So this is origin. So if the circle is of radius 1, so this becomes 1 comma 0. So what is x1 here? 1. r1 here is 0. R is 1. So if you want to validate this, just put these points here. X1 square is 1 square plus x2 is 0 square is equal to 1 square. So that becomes 1 is equal to 1. You can take any point, this point, it becomes 0 comma 1. Apply in this, they will be equal. So this is the generalized form of a square. You are extending that square to n dimensions. So that becomes hypersphere. That's a mathematical representation. And what is the difference between hypersphere and hypercube? Hypercube includes all the points within this radius. That is the reason less than or equal to. When it is equal to, that is all the points on this surface. When it is less than or equal to any point inside that surface, any surface inside that radius r would become this one. So that is the reason for hyperball, we are just adding less than or equal to. So when it is equal to r square, we are talking about this surface. When it is equal to less than or equal to r square, okay. When we are talking about circles less than or equal, this is circle at r square. When we are talking about circle less than or equal to r square, so this is less than r square. This is the all the points inscribed are less than r. This is r less than r. I mean, we are also including all of this into our space. Then it becomes hyperball. Okay, so that is the mathematical representation between hypercube, hypersphere, and hyperball. Understood? Is this clear for everyone? The mathematical representation of the three diagrams that we have discussed. And if you go to the next thing, we just have to understand what is a gamma function, because to derive the next things, we have to understand what a gamma function is. So gamma function is a generalization of the factorial function for complex and real numbers. Okay. Gamma function defined as, gamma function is defined as n minus 1 factorial. Gamma of n is equal to n minus 1 factorial. Okay. That means gamma of 4 is. So this formula is valid for positive integers. Okay. For positive integers. Integers means 1, 2, 3, 4, 5, 6 are called as integers, and they have to be positive. So when you pick up a positive integer, so this formula will be applied. Gamma of n is equal to n minus 1 factorial. So gamma of 4 is equal to 4 minus 1 factorial, which is 3. 3 factorial is nothing but 3 into 2, which is equal to 6. Okay. For non-integer values, the gamma function extends this concept, and it is identified by the following integral of z greater than or equal to 0. So this is the formula for non-integer values. So if we have non-integer values, the example of non-integer is 5.5 is an example of non-integer values. Okay, so to solve this is little complex to solve the integration stuff, right? If the z is 5.5, I have to say t 5.5 minus 1 e to the power of minus t dt. I just, if z is equal to 5.5, which is non-integer, I just have to put this formula 5 minus 5 minus 1 e to the power of minus t into dt. So I have to integrate this. So I have to use chain rule, t to the power of 4.4 integral of 0 to lambda e to the power of minus t into dt, and then minus e to the power of minus t integral of t to the power of 4.5 into dt from 0 to infinity. This is what chain rule says is right. So we have to solve all this stuff, which is really difficult, and we don't need that complex stuff to understand what we're going to do or what we're going to study. Anyways, just try to understand, in machine learning, we never bother about big calculations. Okay, that will all be done by softwares, but you just have to understand the basic concept, like what has to be applied here. When you know gamma has to be applied, the system will help you to calculate that gamma value of any integer, right? But at least you have to know, for doing this stuff, you have to calculate the gamma value, and then you can say to the system that, okay, this is my gamma and this is the value of gamma that I need. So do that. So it will do it for you. So the only thing is you just have to understand the intuition behind it and when to apply what you have to know. So that's the reason calculations are not important, but some derivations are important for you to understand and apply for any concepts that come across to you. So that is the reason I'm trying to explain you the intuition most probably for every thing. So even if you do the calculation wrong, it doesn't really matter until unless you apply the concept in the right way. Okay. Um, right. So some of the properties of gammas is these are the formulas that we're going to apply to solve the basic things, and I also show you how we actually do that. Okay. So we are talking about higher dimensions. When you say higher dimensions, we are always interested to calculate the dimension at infinity. The values at infinity is what we are all interested about in today's class. Till now, we have studied 2D, 3D, and all, but the ones that we have learned so far, learning about how a hypersphere looks like, hypercube, square, rectangle representation of I mean, the mathematical representation of that is also important because, as I told you, geometrical representation and interpretation in higher dimensions is not at all possible. So that is the reason we are always concerned about mathematical representations and how do we use them to apply dimensionality of infinity. Okay, so that's the reason mathematical representations is all what we deal with in coming forward, because we are dealing with high dimensional spaces. Geometrical representation is typically tough in higher dimensional spaces. We also have seen what we have seen example of higher dimensional space. Document comparisons is the best example. So from now onwards, you will do the derivations for all that stuff. So I have kept blank slides just to show you the derivations of all that stuff. Okay. Right. So going back here, the properties of gamma is, this is the factorial property, gamma of n. When n is positive integer, gamma of n is equal to n minus 1. And recurrence relationship, this is the recurrence relationship which we will use to solve the non-integer values. Instead of applying this bigger formula, this property can be used to solve the non-integer values. Okay. So I'll just show you an example for this, but these are just values. Gamma of 1 is equal to 1, gamma of half is equal to root pi. Okay, gamma of 1 is equal to 1, gamma of 1 by 2 is equal to root pi. Remember this. So for this formula to apply, we just have to understand, we have to know this thing. So this formula always tries to get to this value. Okay, that is how we actually solve this. So gamma of z plus 1 is equal to z into gamma of z. Now we are trying to solve for 5.5, gamma of 5.5, right? So 5.5 can be written as 5.5 plus 1, right? Gamma of 5.5 can be written as gamma of 4.5 plus 1, right? 5.5 is written as 4.5 plus 1. So this becomes z plus 1. So this becomes z as z of gamma of z, right? Z of gamma of z. Look at this, z plus 1, z is 4.5 plus 1. So this becomes z gamma of z. So z is 4.5, gamma is gamma of 4.5. So 5.5 can be converted to 4.5 into gamma of 4.5. Now gamma of 4.5 can be converted to 3.5, 3.5. 3.5 can be converted to 2.5, 2.5. 2.5 can be converted to 1.5, 1.5. Okay. 1.5 is nothing but half into gamma of 1 by 2, right? So gamma of 0.5 is nothing but 0.5 gamma 0.5, right? 0.5 is nothing but 1 by 2. Now we know the value of gamma 1 by 2, which is root pi. So gamma of 1.5 is 1.2 root pi. Apply this here. So that becomes 1.5 into 1 by 2 root pi. Apply this value here. Apply this value here. Apply this value back here. So that becomes the value of 5.5. That is how we solve the complex, non-integer values. Understood? This is very important because this is what we use in derivations. Is this clear? Hello?
Yeah, clear.
Okay. Now This is a generalization of, we call this as Stirling's approximation. For non-integer or very large inputs, gamma of z can be approximated to root of 2 pi z, z by e whole to the power of z, where z tends to infinity. When z is very large, which is our interest today, we are always dealing with infinite dimensions or infinite spaces. So that can be approximated to root of 2 pi z, z by e whole to the power of z. Okay, root of 2 pi z, z by e whole to the power of z. That is the approximation of gamma of z in higher dimensions. Okay, so this is just something to memorize, and the derivation of this is not really important for us. This is Stirling's approximation. So that is one of the theory which is approximated gamma of z to this value, root of 2 pi z, z by e whole to the power of z. Okay, so with this, we are done with this slide, and next, just go back to next slide. Okay, now we are trying to calculate, okay, volumes in higher dimensional spaces. Okay, volumes in higher dimensional spaces. That is all what we will learn now. Okay, so we have learned about three different spaces, right? Or diagrams. One is hypercube, hypersphere, and hyperball. Let's try to understand these two things in detail. Okay, let's start with hypercube. Okay, let's leave about hypersphere and hyperball. Let's talk about hypercube. Hypercube. So if you're taking the square, what is the area of the square? If I call this as, what is the notation here, n, right? So if I call this as n, what is the area of this? What is the volume of this, square? What is the volume of this? What is the volume? Volume is nothing but the area inscribed within the diagram, right? So which is equal to the area in 2D space. In 2D, volume is equal to area. Is that right? Do you know what is the area of square?
A square.
Hmm?
A square.
N square, right? And what about cube? What is the volume of cube? And this is in 2D, right? And this is 3D. What is the volume of cube?
N cube.
N cube. And now let's take the cube in higher dimensional spaces. Let's say I have d-dimensional space. What is the volume of this? In 2D, it is n square. In 3D, it is n cube. What is
N power
the
3.
volume of a cube in d-dimensional space?
N power 3.
What is that?
N power 3.
N power d. So it is just like d-dimensional would be n to the power of d. So in two-dimensional space, it is n square, 2, 2. Three-dimensional, 3, 3. D-dimensional, n to the power of t. Okay. If it is a unit hypercube, what is the volume of it? If it is unit hypercube, what is the volume of it? Unit hypercube, what is the volume of hypercube?
1.
1. Reason is n is equal to 1. That implies 1 to the power of t, which is equal to 1. So the volume of hypercube volume of unit hypercube is always equal to 1. So that is what this is. So that is the reason we are seeing it as 2 to the power of n. Why 2 to the power of n? each side of the hypercube has length 2. Okay, it is given that n is equal to 2. When it is given length side, I mean the length of each side of a cube is 2. So that becomes 2 to the power of d. Okay, so 2 to the power of d. N is nothing but the number of dimensions here. Okay, d is just replaced by n. N is nothing but in n dimension. Look at this. In n dimension, it is 2 to the power of n. Now coming back from this to this, so what is the value of what is the volume in one-dimensional spaces? Just try to derive from this one. Okay, just derive from this formula. Just apply n is equal to 1, that becomes 2, right? So if you apply n is equal to 2, 2 square. If I apply n is equal to 3, 2 cube. So that is the volume of cubes in all the spaces, right? Is this clear? Is this clear? Please let me know if you are not able to understand something. I can explain that again. But let me know if you're able to understand. I mean, you're clear with that or not.
Yeah.
Everyone?
Yes, it's clean.
Okay. So now let's talk about hypersphere. Okay. Let's talk about hypersphere. We concluded hypercube now. Let's talk about hypersphere. What does hypersphere actually looks like? In 2D, what is the hypersphere looks like? In 2D, it is a circle, right? In 3D, it is a sphere, right? In 3D, it is a sphere. In 4D, we have seen that larger diagram. We are not bothered about 4D. We are bothered about d-dimensional spaces. Okay. Or n-dimensional spaces, whatever it is just a variable. Now, what is the volume of hypersphere in two-dimensional space? In two-dimensional space, it is just the area, right? Volume is nothing but the area. What is the volume of 2D in, what is that? In 2D, what is the volume of this?
One.
What?
One.
This is a circle, and we are talking about the inscribed
Ball.
area inside this. So that becomes area of a circle. What is the formula of area?
Pi r square. Pi r square.
What is the volume of a cube? I mean sphere.
Volume of the
Sphere.
1 by 3 pi r cube.
What?
1 by 3 pi r cube.
1 by 3 or 4 by 3?
4 by
4 by 3.
4
4
Any
by
sphere
3
1 by 3
pi r cube, right?
pi r cube.
Okay, just look at this. 2, 2, right? 3, 3. And for d-dimensional, we know it is RD, right? Let's leave about this. We are not sure about this, but this is RD, right? This becomes RD when you compare this way. Okay, is that right? I'll call this as KD. I'll call this as a constant. So this is a constant, this is a constant. I'm generalizing this as constant KD in higher dimensional space. And this becomes R square R cube R to the power of D. Okay, so this becomes R to the power of D. Right? So volume of hypersphere in higher dimensions is R to the power of n. If it is n dimensional space, it is R to the power of n. So we are talking about constant, right? That constant is defined as pi to the power of n by 2 by gamma of n by 2 plus 1. Okay. So that KD is defined as, that KD is given by pi to the power of n by 2 by gamma of n by 2 plus 1. Okay. So now to find out volume of any n, we just have to know to solve the gamma, right? That is why we have learned all these formulas to learn how to solve this gamma for different values of n. Okay, so we will actually do that, how to actually solve it, how to actually solve this n by 2 plus 1. But let's come back to this. So volume of sphere, we know, now we derived, I mean, we know what is volume of n. It is just proportional to r to the power of d. Because how do we derive that? We just have seen this trend and we marked in d-dimensional space, it is proportional to rd, and this constant kd is something given by some approximation, which is a pi to the power of n by 2 by gamma of n by 2 plus 1. Okay, so now what is the difference between sphere and a hyperball? Sphere and hyperball is nothing but sphere just focus only on the points within the with a distance of radius r, right? But when it comes to volume, we are calculating this space. Volume is nothing but the space inscribed within a particular diagram. If it is a sphere, we are just talking about, when you say volume, the volume inscribed within this sphere. So when we are talking about volume, hyperball and hypersphere would be same, right? Because we are talking about the entire thing inside that included is called as a volume. What does volume mean? Volume is nothing but what is the space occupied within that within that particular diagram is called as volume. So when you say hyperball and hypersphere are same, except that hyperball will have will include points within it, or uh, include points within it. But when it comes to volume, we calculate everything inside that to actually derive the volume, right? When you bothered about only the surface, that is called a surface area. Yeah, for circle, we call that as perimeter. But when you bothered about only surface, when you bothered about only this surface, that is called a surface area. But volume actually bothers about the area inside that also. Okay, volume bothers about the entire space within it. Okay, the entire space within it. But surface area is bothers about only the space here, that we call that as perimeter or surface area on the outer circle. It doesn't bother about the area within this, inside that, or the volume inscribed within the diagram. So that is the difference between volume and surface. So now we know the difference between hypersphere and hyperball is just the space within it. When volume is considering the space within it also, then hypersphere and hyperball will be equal, right? So that is the reason, if you look at the volumes of both hypersphere and hyperball, they both will be equal. Because from a structure's perspective, they both are equal. The only difference is hyperball will also calculates or also considers the area within it, or the material inscribed within it. So but hypersphere will just consider the points outside it. But when it comes to volume, they both will be the same. Agreed? Hello? Did you get me? You want me to repeat that again or what? Understood or not? Hello?
Yeah,
Not clear?
yeah, not clear.
Yes.
Yeah, it is just like, just look at this example. So we know hyperball and hypersphere, right? Well, the only difference between this is, so we need to differentiate this in two things. So when you say a diagram, any diagram, let's talk about a cube. When you say volume, volume is nothing but how much, let's talk about uh, a bucket. Okay, let's say when you let's take an example of bucket. Okay, when you talk about the volume, when you pour some water inside this, how much space or how much water that can be filled is what volume actually defines. Okay, so volume always calculates that being filled. Okay, if something is filled inside this bucket, how much is the how much water that it actually can fill within it. So that is what volume actually means. Okay, how much space that is available within it, that it is including everything inside it, how much water it can be filled within it. Okay, similarly, when you take the sphere and a hyperball is already filled with water. Okay, because it is the inside of it has to be filled already. Okay, so the inside of this should be already filled. That if that is filled, then only we call that as hyperball. But hypersphere is something inside is not filled. So what we when you calculate volume, you have to fill it with something, and then that only gives the value of volume. But if you take the hyperball, you don't have anything to fill, so you doesn't actually need to fill it, but you will just calculate the volume of it, already filled material. So you just have to calculate how much is filled. You can just take out the water out of it, or can calculate the volume of it, or again but in this case, for you to understand the volume, you have to fill the water, and then only how much water got filled inside this is something which helps you to calculate the volume of it. So I will put it this way. So hyperball, what is the difference between hyperball and hypersphere? Hyperball will comes when the water is already filled inside it. Okay, if the water is filled inside that ball, then only that will be called as hyperball. The only difference between hypersphere and hyperball is, if you take this example, a ball filled with water is called as hyperball. It should be already filled. If the water is not filled in the hyperball, it is called as hypersphere. If the water is not filled in this ball, we call this as hypersphere. Now what we are trying to calculate, you're trying to calculate the volume. How you calculate the volume? You pour water inside that space which is empty, and then calculate the amount of water that got filled. That gives the value of the volume for you. As this is empty, it's your job to fill the water and have to calculate that water to see the volume of this hypersphere. When you come to hyperball, you have already water filled within it. What you just have to know, you have to know how much water is filled inside this is what you have to know. Okay, it is just like filling the water and not filling the water, except that there is no difference. When you're calculating volume, you always calculate volume for a filled space. Okay, so in that case, you are including the all the empty space within this also to calculate the volume. So the statement that I'm putting forward is, when it comes to volume, hypersphere and hyperbolas are same. The reason being, we are calculating everything inside it. Okay, if it is just because water is not there, it doesn't mean like you will not say volume as zero. You have to fill the water, and you have to say this much water is filled inside this, so that would become the volume of this hyperball. As the water is already filled inside this, you doesn't actually need to fill it, but you just have to know the quantity of water actually filled in it to make it as a hyperball. Understood?
Yeah.
So when it comes to volume space, when it comes to volume, hyperball and hypersphere is same. But when it comes to surface area, only hyperball will have the surface area. So hyperball is just the points within this, right? So when you calculate volume, you calculate everything inside it along with the surface. Okay. When you calculate only, when you're considering only hypersphere will only have this surface area. So if you take the example of square of a circle, the area of this is pi r square, but perimeter of this is 2 pi r. Do you know what the perimeter is? Perimeter is just this ring's length. Okay, the area is pi r square, which includes everything inside it. Okay, if you just want to understand this better, look at this. So this, the radius of this is r, right? And you know the perimeter, this circle perimeter length is 2 pi r. And if you want to find out the area inside this, you have to integrate this from 0 to r, 2 pi r dr, right? This length 0 is extending from 0 to r. Okay, so what does this mean? Like, we have to calculate the integral from 0 to r. The reason being, look at this. So this is outer circle, and this is the inner circle, and this is inner circle, and this is inner circle, this is inner circle. When you combine all of this lengths together, it forms the area inside it. Okay, so that is the reason this circle, outer circle, which is 2 pi r, is going from 0 to r. So all these circles, it starts from 0. It's a 1, 2, 3, 4 till to r. So it goes from 0 to r, 2 pi r and dr. If you integrate that, you will get the area under this. So if you integrate that, what happens? 2 pi is a constant that comes outside. So 0 to r, r dr. So that is equal to 2 pi. Integral of r is r square by the 2. And you have to apply from r to 0. So if you apply r here, that becomes 2 pi r square by the 2 minus 2 pi into, when you apply 0 to r, it becomes 0. So 2 will cancel, pi r square. So that is the area of this diagram, right? So 2 pi r is just the surface area. When you integrate from 0 to r, it becomes the area. In 2D, area is also called as volume. Okay, so that is 2 pi r. So this is the surface area of the cube, right? So look at this. Volume has r square, and uh, the surface area, which is perimeter, has r, which is equal to -1 to the actual dimension. This is 2D. In 2D, volume has 2, but perimeter has 1 less than it. So if you look at this, the surface area of a circle is equal to r to the power of n minus 1, 1 less than the dimension of the volume. Okay, and this is also a constant. Okay, for 3D, the surface area becomes r square. Do anyone know what is the surface area of an sphere? Surface area of sphere. I just have to find out the formula of surface area of sphere. Four by r square.
4 pi r.
Okay, volume is 4 by 3 pi r cube. Look at this, n minus 1. So the same comes here, r to the power of n minus 1. This constants are derived. Look at this. This is one of the constants in 2D. In 3D, this is constant. In 2D, this is constant. So in d-dimensional, it is constant kd r to the power of d minus 1. If there are d dimensions, it becomes d minus 1. So kd r to the power of d minus 1. So that is the surface area given over here. Now you got everything. You got all the formulas. You understood hyperbol's volume, hypersphere's volume, and also surface area. You are just trying to get this r to the power of n, right? You are, I mean, deriving this r to the power of n based on the lower dimensions, right? Now your job is this. What is your job now? You also got the constants. How does the constant value looks like in higher dimensions? It is pi or n to the power of n by 2, gamma n by 2 plus 1. Now it is given like this. Gamma of n by 2 is nothing but, so you're now you know the value of n by 2, right? It is easy. If n is equal to 2, 2 by 2, it becomes pi. But you have to calculate gamma of n by 2 plus 1. So gamma of d by 2 plus 1 is given as If d is even, it is d by 2 factorial. If d is odd, the formula given is root of pi into d double factorial by 2 to the power of d plus 1 by the 2. What is d double factorial? D into d minus 2 into d minus 4, so on 1. D factorial, we all know, it is d into d minus 1 into d minus 2 to the power extending to 2 into 1. So we know the factorial, normal factorial, but double factorial is nothing but instead of 1, the minus will be like 2, 4 even numbers. That is what double factorial means. So we using these formulas, we can calculate the, you know, the value of gamma of n by 2 plus 1. Okay. But so let's suppose if you are given d is equal to 2, it becomes 2 by 2 factorial, 1 factorial, which is 1. So this becomes 2 double factorial means 2 double factorial means what does that means? Like 2 into 2 minus 2, which becomes it don't go to 2 minus 2, right? It just stays at 2 only. What is the double factorial of 2? When 2, I mean, when, this applies only for d is equal to what? Let's suppose d is equal to 3, that becomes 3 into 3 minus 2. That becomes 3 into 1, which is equal to 1. Okay. So that is what double value calculation. Let's suppose if it is 5. 5 into 3 into 1. Factorial, it's suppose 5, if I say 5 factorial, 5 factorial is nothing but 5 into 4 into 3 into 2 into 1, right? When you say 5 double factorial, it is 5 into 3 into 1. We are skipping the even numbers here. Okay. So this is applicable only when d is equal to what? This formula is applicable only when d is equal to what? So double factorial is valued only for d is equal to what? We are bothered about double factorial when only when d is equal to what? So we got these formulas like gamma of d by 2 plus 1 is equal to d by 2 factorial if d is on, and this is the formula. Now you just have to derive these formulas. Okay. You know these things, right? You know these things, and using these properties you have to derive these things. So I'll give you a couple of minutes to try on your own, and if you're able to solve these things, post it in the chat, or else I'll show you the derivation for this. Okay. So what we are trying to do here, we are trying to do gamma of d by 2 plus 1. So we are talking about d as even. D as even. So we know gamma of n plus 1 is equal to n into gamma of n, right? So we know this formula from this screenshot, like gamma of z plus 1 is nothing but n into gamma of z, z into gamma of z. So the same applies for n plus 1 is equal to n into gamma of n. So this becomes d by 2 into gamma of d by 2. So when d is even, what does this become? When d is even, what does this becomes? This becomes an integer, right? Take any value of t which is even. If d is even, take any value of t, this becomes 2d. I mean, d by 2 becomes an integer, right? Right or not? Take d as 6, 2 by 3, 6 by 3. 6 by 2 is, sorry, if d is equal to 6, an even number, 6 by 2 is 3. We will get an integer. D can be anything. Let's take d as 500, which is even number, right? By 2, that becomes 250, which is even again an integer, right? So when d is even, d by 2 will always become an integer. When when n is an integer, when z is an integer, what is the formula of gamma of n when z is integer? What is the formula of gamma n when z is integer? So gamma of n when n is integer can be written as n into, it's n minus 1 factorial, right? N minus 1 factorial. Look at this. Gamma of n for positive integer n, gamma of n is equal to n minus 1 factorial. I'll go back here. Gamma of n is equal to n minus 1 factorial. So now this becomes, as we know, this is d by 2 is an integer. Let's call d by 2 as n. Okay. So that becomes n minus 1 factorial. So d by 2 is there, and gamma of d by 2 will become n minus 1 factorial. So that becomes, so this is n minus 1 factorial, right? So that becomes d by 2 into n minus 1 factorial is nothing but n minus 1 into n minus 2 into n minus 3, so on 1, right? So I'm going to replace back n with d by 2. So this becomes d by 2 minus 1. So d by 2 minus 2, so on till 1, right? So now if you look at this whole thing, this becomes d by 2 factorial, right? D by 2 factorial is nothing but d by 2 into d by 2 minus 1, d by 2 minus 2, so on up to 1. So if n is even, gamma of d by 2 plus 1 will becomes d by 2 factorial. Okay. So that is what it is given over here. Gamma of d by 2 is d by 2 factorial if d is even. Got it? Now we have to derive the second part. Gamma of d by 2 plus 1 is equal to root of pi into d double factorial by 2 to the power of d by 2, d plus 1 by the 2, if d is odd. So now we have to prove that part. Okay. So how does that looks like? So we are trying to solve d of gamma of d by 2 plus 1 when given that d is odd. Okay, so d is odd in this case. Okay, so again this can be written as d by 2 into gamma of d by 2, right? D by 2 into gamma of d by 2. And now we know d is odd. When d is odd, what happens? This becomes a non-integer value, right? This becomes a non-integer value because 6 by, if d is even, d is odd means 5 by 2. 5 by 2 becomes 2.5. 7 by 2 becomes 2. What does this becomes? 3.5. 5 not 1 by 2 becomes 250.5. Okay. So that is how deep actually looks like. Look at this 0.5. How did we solve 2.5? When we are here, this 0.5 is how are we solving? We are just converting that to the number 1 value gamma of d 0.5. Okay. So just look at this. We are doing -1 for this, putting over here, and -1, -1, -1, so on to root pi, right? So gamma of 5.5 can be written as, how are we writing this? 4.5 into 3.5 into 2.5 into 1.5 into root pi, right? This is how you're getting the value of that. So I'll use the same technique here, similar to that. How can I write this? D by 2 into d by 2 minus d minus 1 by 2, d minus 1 by the 2, right? I'm just taking -1 from this and multiplying so on. D by 2 -1 into d by 2 -1 -1 -1 so on up to root pi. Can I write this way? Just take this example. If we have 0.5, anyways we get 0.5. Whenever we divide an odd number by 2, we always get 0.5 at the end. Take any even number. I mean, take any odd number. When you divide odd number by 2, we always get 0.5 at the end. So when you're getting 0.5 at the end, how are we deriving this? So how are we translating that? It becomes 4.5 gamma 4.5. Gamma 4.5 is nothing but 3.5 into gamma 3.5. It's nothing but 2.5 into 2.5. This becomes 1.5. So 4.5, 3.5, 2.5, 1.5 into root pi, right? 1.5 into root pi by the 2. Okay, 0.5 into root pi by the 2. So what we are doing, we are just doing minus, we are starting with -1 of this thing, and we are doing -1 for this value, we are doing -1 for this value, -1 for this, going back, this becomes 0.5 into root pi, right? So now the same I am applying here. I know this is 0.5, right? I know this is 0.5, this becomes 0.5. So I have to take -1, and to this value I have to take -1, to this value I have to take -1, so on up to 1 by 2 into root pi. Now what does this become? D by 2 into D minus 2 by 2 into D minus 4 by 2 into D minus 6 by 2 into so on root pi by 2, right? This becomes D by 2 minus 2. -1 becomes -2. 2 into 2 becomes D minus 4 by 2. This is D minus 2 by 2, D minus 4 by 2. This becomes -3. 3 into 2 is 6, D minus 6 by 2. So if I take numerator, look at this, D minus 2, D minus 4, D minus 6. What does that say? D double factorial, right? D double factorial is nothing but D minus 2, D minus 4. Look at this, D double factorial is nothing but D minus 2, D minus 4, so on 1. So if we got 2, and at the end you have root pi into D double factorial by 2 to the power of, okay, how much, how you have these things, right? How are we getting D plus 1 by 2 is what you have to understand. How are we getting D plus 1 by the 2? How to show this to you? Let's take a simple example, right? So that will actually solve your problem, right? Let's take DS7. I'm taking DS7, which is an odd value. And I'm trying to calculate the gamma of 7 by 2. So what does that will become? What does that become? It becomes 7 by 2 into 5 by 2 into 3 by 2 into 1 by 2 into root pi, right? So for 7, how many 4s I'm getting? 2 to the power of 4 I'm getting, right? So for 7 I'm getting 4. So can I write 4 as D plus 1 by the 2? So D is 7, 7 plus 1 by 2, which is 8 by 2, which is 4, right? So does that make sense? So 2's are coming to be 2 to the power of D plus 1 by the 2, right? Is that right? Right? So this 7 by 2 is nothing but I added for this D by 2. So gamma of 7 by 2 starts from 5 by 2, 3 by 2, 1 by 2. So including all of that will become 2 to the power of 4. Okay. Gamma of 7 by 2 is nothing but 7 minus 1 by 2. It starts from here. Gamma of D by 2 starts from this one. Gamma of, D by 2 starts from this one. So when you say 7 by 2, it becomes 7 by 2 minus 1. It starts from here, goes up to root pi. But we are bothered about only 2's in the denominator, right? For gamma, we got 3 2's and we have D by 2 before. For 1, 2 we got. So total 2 to the power of 4 for 7. When d is equal to 7, we got 2 to the power of 4. So this 4 can be written as d plus 1 by the 2 when generalizing for higher dimensions. So 2 to the power of d by 2, 7 plus 1 by the will be 4. So that will become 4. So I say d plus 1 by 2. So that is what the derivation for this one. If d is equal to what? That becomes root of 2 pi d double factorial by 2 to the power of d plus 1 by the 2. Okay. So that is how gamma of d plus 1 by 2 will be derived. So if you remember the formulas, that should be good. If you don't remember that, you can simply derive or calculate this way. Again, calculations are not your part, but you just have to understand how we are using gamma functions for solving the even case and odd cases. Maybe for if this is not available for you, you can just apply these formulas. If the computation of it all comes down to computation when you're using mm, a system. So when you find out like all your n values are just evens, okay, your n values don't have an odd values, you're always taking only even values, you can just replace gamma of n by 2 with d by 2 factorial, so that computation will much become easier when compared to gamma of n by 2. That is as simple as that. Now we know all this stuff, right? Can you bring back these formulas from these formulas now? So now n is equal to 1, 2 to the power of uh, this becomes 2 pi root of 1 by 2, 1 by 2, n is equal to 1, so that becomes 1 by 2, r to the power of n minus 1, n is equal to 1, so that becomes r to the power of 1 minus 1 will become 0 by gamma of n is equal to 1 by 2. Gamma of 1 by 2 will be, what is the formula of gamma 1 by 2? 2 root pi into r is equal to r to the power of 0 will be 1, and I'm just trying to apply the formula back, that's all. Gamma of 1 by 2, what is the value of gamma 1 by 2? Gamma 1 by 2, it's root pi, right? Gamma 1 by 2 is root pi. So we got gamma 1 by 2 here. So we got root pi. So cancelling both of them, so the surface would become 2. For one dimensional sphere, we got it as 2. But one dimensional sphere is nothing but a line, right? For that, we are getting it as 2, constant 2. Surface area. Basically, surface area would not be considered. Like if you calculate for two dimensions it is circle, and we know the formula for two-dimensional sphere is, I mean, the surface area for this circle is 2 pi r. Now let's see if you're getting 2 pi r or not. So apply n equal to 2 for this formula. This becomes 2 pi 2 by 2 into r to the power of 2 minus 1 by gamma of 2 by 2. Okay, so this becomes gamma of 1. You know gamma of 1 is equal to 1. So gamma of 1 by 1, gamma of 1 will be 1. So this is 1. This becomes 2 to the power of pi into 2 by 2 is 1. R to the power of 2 minus 1 is r. So that becomes 2 pi r, which is matching to this actual value. So that is how you calculate the surface area. Now if you calculate the surface area for 3 dimensionals, what you will get? You know the surface for area for 2 dimensions, right? What is the formula for surface area for 2 dimensions? We just have seen that. What is the surface area for 2 dimensions? Hello? What is the surface area for 2 dimensions? we have seen, right, something like 4 pi r square, right? That's what we have seen. Surface area for 3 dimensions. Now apply the surface area for 2 dimensions. It becomes 2 pi, n is 3 by 2, r to the power of 3 minus 1 will become 2 by gamma of 3 by 2. Okay, so n is equal to 3 by 2. So this becomes 2 pi 3 by 2 into r square by gamma of 3 by 2. What is the value of gamma 3 by 2? So this becomes 3 by 2 minus 1 into 1 by 2 root pi, right? That is what we get for 3.2. So 3.2, 3 by 2. So 3 by 2 is nothing but 1.5, right? So what is gamma 1.5? 1.5 is nothing but 1 by 2 root pi. So this is already become 1 by 2. So gamma of 1 by 2 is nothing, 1.5 is nothing but 1 by 2 root pi. So we can get rid of this thing. So 1 by 2 root pi. So this pi goes back, I mean this 2 goes to the top. This 2 goes to the top, that becomes 4. And root pi will be 3 by 2 minus 1 by 2, right? When this root pi is nothing but pi 1 by 2. Pi to the power of 1 by 2. If this goes to the numerator, this becomes minus 3 by 2 minus 1 by 2 into r square. So that is 4 pi 2 by 2, right? 3 minus 1 will become 2 by 2. That will become pi, 4 pi r square. So we already know the formula for this 4 pi r square. So similar way, you can calculate the volumes of all of this. Okay. And you will get the same formulas that you have seen. I can just do volume of one dimension so that you can just figure out the rest of the, you can actually give a try for rest of the things. So let's calculate the volume of three-dimensional sphere. Okay, volume of three-dimensional sphere or hypercube, it is something like n is equal to 3 pi to the power of 3 by 2 by gamma of 3 by 2 plus 1, gamma of 3 by 2 plus 1 into r to the power of 3. Okay, so this is what we have to calculate. What is the value of 3 by 2 plus 1? N is odd, right? Here n is odd. When n is odd, what is the formula? It is nothing but root pi into 3 double factorial by 2 to the power of 3 plus 1 by the 2. So that becomes pi to the power of 3 by 2 r cube by root pi into 3 double factorial means what is the value of 3 double factorial? 3 into 3 minus 2, right? So that becomes 3 into 1. So that becomes 3 by 2 to the power of 2. Right? 3 plus 1 is 4. 4 by 2 is 4. 4 by 2 is 2. So that becomes 2 square. So if this goes up, this is in the numerator. So this will go into the top. That becomes 4. 5 3 by pi 3 by 2 into root pi becomes 3 by 2 minus 1 by 2. So what does this looks like? Pi 3 by 2 by root pi. So that is equal to pi 3 by 2 minus 1 by 2. Root is nothing but 1 by 2. So if this goes to numerator, that becomes minus 3 by 2 minus 1 by 2 becomes 3 minus 1 by the 2. That becomes pi. 3 by 2 is 2 by 2 minus 1. That becomes pi. So this whole thing will become pi. R cube. In the denominator, we have 3. 4 by 3 pi r cube. Okay. That is how you're going to calculate the volumes using these formulas. Okay. So the same volume applies for hypercube and hyperball as well. So in n dimensions, these are the formulas that will be applicable. And we use these formulas to derive uh, few assumptions. So few statements will be derived from these formulas. So we are going to frequently use these formulas in the next slides. And we also have seen solving these formulas now, right? So going back to the next slide. So we have derived the gamma function from previous slide. in this particular slide. Now going back here. So the next three slides are very important. These are the assumptions that we're going to make. Okay. We are left with a few more today. Right. So going back to this one. Going back to this one, which is what happens to the volume of hypersphere when dimension goes to infinity? And now we know what is the volume of hypersphere. We know the volume of hypersphere is this formula, right? We got this formula. This is the volume of hypersphere. Pi to the power of n by 2, r to the power of n by gamma of n by 2 plus 1. So I am writing this as pi to the power of n by 2, gamma of n by 2 plus 1 into r to the power of n. Right? This is what the formula is. Now what we are interested in, when the number of dimensions goes to infinity. So this is what we are interested in. What happens when n by 2 plus 1 goes to infinity? Okay. Now let's break this apart and see what happens. What happens to the volume of hypersphere? Okay, if d tends to infinity. Okay, so this is constant kd. Kd is taken as pi to the power of n by 2 by gamma of n by 2 plus 1. Okay, gamma of n by 2 plus 1. Gamma of n by 2 plus 1. Now we are interested to understand what is limit n tends to infinity. Okay, so this goes like this. So this is equal to, now let's replace gamma of n by 2 plus 1 with um, gamma of n by 2 with the values that we know. So it doesn't really matter when n tends to infinity, if it is even or odd, it doesn't really matter. Let's take n as even to simplify our calculations. Even n plus 1, even plus 1 doesn't really matter. Whether it is odd or even, in higher dimensions, it doesn't really matter. So this becomes gamma of n by 2 will become, when d is even, or when n is even, what is gamma of n by 2 plus 1? This becomes n by 2 factorial, right? So that is what we have seen here. So gamma of n by 2 is nothing but n by 2 plus 1 is nothing but n by 2 factorial if n is even. So let's consider n as even, which is equal to n by 2 factorial. Okay. So now what we can do here is, we can approximate this, right? This is what the approximation of factorial of a number in higher dimensions. Okay, so this is the approximation of factorial in higher dimensions. So what I am going to do is pi to the power of n by 2 by, I'll replace the approximation of n factorial in higher dimensions when n is large. Stirling's approximation for approximating the factorial of large numbers. So when n is large, we are talking about n equal to infinity. So when n is large, we are going to do this. When n is large, we will replace that with Stirling's approximation. What is Stirling's approximation says? That says n factorial is nothing but root of 2 pi into n by 2, or n is now n by 2 by n by 2e whole to the power of n by 2. Okay, I'm replacing n by 2 factorial with this approximation. Here n becomes n by 2. So everywhere I'm replacing n with n by 2 now. So here 2 and 2 gets cancelled. N by the 2e whole to the power of n by 2. So now I'm trying to find out what happens if n becomes infinity for this particular, okay, for this particular value. So this is pi to the power of n by 2 by root of pi n is what we have here into n by the 2e whole to the power of n by 2. So this is all what we do have, right? Now I can do it this way. So I can make all these powers equal, right? So this becomes 2 pi e by the n whole to the power of n by 2 into 1 by the root of pi n. Okay, so this is what it actually means now for us. And now if I apply limit n tends to infinity. So if when n is infinity, the 2 pi e value is approximate to 18. Okay, 2 pi e, you can calculate it is less than or equal to 18. So pi is 22 by 7. E value is somewhere around 4.18, I think. You can just calculate 2 pi e if you want. It would be less than 18. The value of e is 2.7 into 3.14 into 2. So 2 into 3 into 2, which is equal to 2.718. Calculate 2.718 into 3.14 into 2. So it is coming as 17.06. Okay. So this value is 3.14. Value of E is somewhere around 2.718. Oh, sorry. Value of E is somewhere around 2.718. So the entire value is coming up as 18. So this is less than 18 and one n value is infinite. So then what does 2 pi e by n will become? 2 pi e by n will become, let's suppose 18 by, say it as 10,000. It is coming close to 0.00018, right? When this n keeps on increasing, this value will somewhere approach to 0, right? This value, complete value goes to 0, right? Agreed with it?
Yes.
So when multiply anything with 0 will become 0, right? So the whole volume when n tends to infinity will goes to 0, right? That is an important observation. Volume of hypersphere goes to 0 when n tends to infinity. That means in higher dimensions, volume of hypersphere is going to 0. Does that look interesting? In one dimension, what is the value of it? In 3 dimensions, it is 4 by 3 pi r cube. If you take r is equal to 1 unit hypersphere, what is the value of this is coming to be? 4 by 3 into pi, which is somewhere equal to 4 by 3 into 22.7. Okay. So 4 by 3 into 3.4, what does that become? 22 into 4 divided by 7 into 3. So this is 4.19, right? In 3 dimensions, it is 4.19. What does this looks like in 2 dimensions? It is pi r square, right? That becomes pi. That is 3.14. In lower dimensions, we have some value. But when you goes to n dimensions, I mean when higher dimensions, we are saying that as 0. Volume of sphere is coming to be 0. Volume is nothing but the amount of area that is available inside it, the amount of space that is available within it. But how does the volume of a sphere is going to be 0 in higher dimensions? That is what mathematics says to us, right? That is what calculus is saying to us. What when you apply Stirling's approximation, you applied when you calculated using Lagrange's theorem, you're getting the volume of hypersphere is going to 0 in higher dimensions. So this is unbelievable, but you have to accept that volume of hypersphere in higher dimensions is 0. That is what mathematical proof is saying, that even that doesn't goes to 0, that will be very, very minimal, right? Some 0 point, some thousand times 0, 18 doesn't make any sense. It is very, very, very less value. I mean, it is going very close to 0, right? Almost equal to 0. We can approximate that to 0. So this is how the volume of a hypersphere actually looks like in the real world. Okay. So the first observation that you have found with all the knowledge that you have given so far is, with all the derivations that you have done so far, is volume of hypersphere in higher dimensions is going to 0. So this is how the volume of a hypersphere looks like. It goes, increases, and at one point it slowly comes down to 0. It may not touch 0, but it goes close to 0. So volume of a hypersphere is higher at somewhere around 5, and then it starts decreasing, and higher dimensions it actually goes to 0. You can just try to see, I mean, when you get some time, you can just apply n5, n7, n8. What you just have to understand, what you just have to derive is, when n is equal, when you see volume at 8 is less than volume at 5, you can conclude that, right? Something is causing for the volume to shrink. Okay, that simple calculation you can do, and you can find out the graph is coming up like this. The volume of sphere will be at 4, this is the value; at 3, this is the value. We see an increase from 3 to 4. At 5, it would be maximum, and after 5 it slowly starts decreasing, and when n goes to infinite, this approaches to 0. This is volume of sphere in d dimensions of radius r. Okay, so this is the notation. Volume of sphere in d dimensions with radius r. And when you talk about unit sphere, r becomes 1. And hyperball is represented like this: volume of hyperball in d dimensions with radius r. Okay, so these are the notations for hypercube and hyperball. Hyperball is represented by b, I think. Hypercube is represented by h of dimension d, of higher dimensions. It won't have radius. Hyperball is represented by b. Sphere is represented by h. Hypercube is represented by ht. Okay, volume of ht. So these are the representations of all the three parameters. Okay, right. So volume of ht. So this is an interesting property in the higher dimensions. Volume of hypersphere in higher dimensions, when dimension is infinity, when dimension is large, it is approaching to 0. Okay, so that is our first observation that we have derived, which is interesting. Now we know the volume of sphere is going to 0 in higher dimensions. Okay, now this is an interesting other observation that we're going to make now. Volume of a sphere with respect to inscribing hypercube. Okay, so we are going to find out something in this. Now I'll give you a simple example before we go derive this. You will when I see this, when I was trying to understand this, I really felt mesmerized, because the findings are really will always contradict to what we actually believe. We cannot actually believe that volume of a sphere will go to 0 in higher dimensions, when the volume of a sphere in of a hypersphere, I would say, in at 4 dimension is around 3.14. I would say somewhere around like 4 that we have got, right? At 4th dimension, it is somewhere around 4.19. How come it is going to 0 at higher dimensions is something which you cannot believe, but that is what you have to believe, and that is how the system is actually really in the highest. And this is another interesting observation which you will find out. Okay. I'll before explaining that particular stuff, I'll just give you a simple example. Let's take a square. Let's take a rectangle or square, whatever it is. I'm taking a rectangle of length 2 into 3. And inside this, I do have another rectangle. Let me change the color, maybe that helps. Let me change the color to red now. And now inside this, I have another rectangle of 1.5 length. Okay. So now you have to tell me how much space you have to calculate how much space this rectangle has occupied in the main rectangle, the blue color one rectangle. The question is clear, right? So you have to find out how much percentage of area is occupied by the red rectangle inside the blue rectangle. How much area that this small rectangle, this red rectangle occupied the main rectangle. Just post your answers in the chat, and also the way you calculated that. I'll be here in just a minute. So what is the volume of this? Volume of the smaller or area of the smaller rectangle. You can also call that as volume in the higher dimensions. But what is the area of this? 3 into 1.5, right? 3 into 1.5 is the area of the inner rectangle. The outer rectangle area is 6, right? So 6 is 100 percentage. Right now we want to calculate 3 into 1.5. That becomes how much that does become? 3 into 1.5, 3, 4.5, right? 4.5. How much percentage is this? Is what we have to calculate. So what we will calculate 4.5 into 100 by 6. Okay, so that is what this is what which gives us the volume occupied by the smaller rectangle in the bigger rectangle, right? If I keep this in the formula, volume of inscribed space by volume of hyperrectangle into 100, right? Volume of this by volume of the entire space by into 100. Does it make sense? Is this how we calculate the volume of the inner rectangle with outer rectangle? It is just this. The 6 is 100 percentage. We want to calculate how much percentage that 4.5 occupied. So it is nothing but 4.5 into 100 by 6. So that gives us this. Now, what we are going to try here is we want to find out the volume of sphere with respect to the inscribed hypercube. Sorry. Yeah, volume of sphere with respect to the hypercube. So we want to find out how much this hypersphere volume occupied with respect to the hypercube. So for that, what you have to do, it is just like volume of sphere by volume of hypercube. So they both share the same, I mean, the length of this would be half of the radius of the sphere is nothing but half of the length of the hypercube. Let's suppose, let's take both of them as hypercubes where radius of this is 1 and the length of the square is equal to 2. Let's do that calculation that way. And this also brings us to a very important conclusion, which is very interesting. For that, this is the where we start. We just want to understand how do we calculate the volume of an inscribed space within the bigger space. Okay. It is all. Now, this is what we're going to calculate now. Volume of sphere inscribed of volume of sphere with dimension d of radius r by volume of hypercube in d dimensions. So this is what we are going to calculate. Okay. So with this in place, and now let's start from 2 dimensions. Okay. In 2D case, what is the volume of sphere? It is nothing but pi r square, right? Pi r square is the volume of this one. So I'm taking the length of this cube as 2 and the radius will be 1. So the radius of this will be 1 because I'm talking about hypersphere. I'm talking about hypersphere. So hypersphere, let's suppose the length of this is equal to 1. Okay. And the length of the whole cube is 2. In 2 dimensions, we are if you calculate the volume of sphere in 2 dimensions, it looks something like this. So this is pi r square. R is equal to 1, so this becomes pi by, what is the volume of this one? 2 into 2, 4, which is 4. Because it is r square, that becomes 2 into 2, which is 4. So pi by 4 is nothing but, what is the value of pi by 4? When you calculate percentage, it becomes into 100. So pi by 4 is nothing but, can someone say me the value of that pi by 4? Pi divided by 4, that becomes 78.5, right? When you convert that to percentage, it becomes 78.5 percentage, right? So the volume of sphere, the volume taken by the sphere is 75 percentage of volume that cube has. So what does that says is only 25 percentage of area is occupied by these corners. So these corners has just 22 percentage of volume, and this sphere has 78.5 percentage of volume. Okay, so if I draw this diagram for your better understanding, so if this is the cube and this is the sphere inside it, this has 22 percentage, this has 22 percentage, this has 78 percentage, somewhere around. Okay, so that's interesting. Let's go back to 3D. In 3D, what is the formula of volume of cube? 4 pi 3 pi r cube, right? R is 1, so 1 cube is nothing but 1. And coming to the volume of cube, it becomes 4 cube, I mean 2 cube, right? The dimension is 2, so that becomes 2 cube. Volume of sphere in 3D is 4 by 3 pi r cube. R is equal to 1 because the radius of the sphere is 1. So that it becomes 1 whole cube is equal to 1. 4 by 3 pi r cube, 4 by 3 pi by 2 cube. So that becomes 4 by 3 into pi by 8. So that it becomes 4 by 4 ones are 4, 4 twos are 8. So that becomes pi by 6. What is the value of pi by 6? What is the value of pi by 6? 52.35 percentage, somewhere around 52 percentage. So when we go to 3D, what is happening? When we are going to 3D, so this, if this is the 3D diagram, inside this I have a sphere, and that sphere is occupying 50 percentage of area, and the corners in the 3D, I mean the similar corners, you're putting a ball inside a big room. Okay, that ball, that sphere inside that room is touching the floor, ceiling, and both the walls, and you will left out with some space in the corners, right? Once the ball is occupied, that corners has 50 percentage of area. Okay, so look at this, the corners area is, I mean the sphere occupied area is decreasing, the corners area is increasing. What does this is? When the sphere occupied area is decreasing, the corners area is increasing. That is what you have to observe. And now let's go to D dimensions and find out what happens in the D dimensions. Okay, in the D dimension, what we have, we have KD, the constant, by RD, right? R to the power of D is the volume. KD into R to the power of D is the, let's look at this formulas again. So what is the volume of sphere in D dimensions? This, I call this whole thing as KD. Okay, this is somewhere constant. This is KD and R to the power of D by, what is this? If this is two-dimensional space, 2 to the power of n. Okay, so this is what it gives to us, to KD R to the power of D by 2 to the power of D. Let's suppose if it is L to the power of D, but now my length of the cube is 2 to the power of D, so this becomes 2 to the power of D. And R is equal to 1 in this case, so this becomes KD by 2 to the power of D. Okay, now I have to apply limit D tends to infinity, KD by 2 to the power of D. And do you remember we derived this limit d tends to infinity? What is kd in the previous slide? Why is that arranged? Okay. So do you remember we derived this? We applied even for that, and we came up with 2 pi e by something. 2 pi e is less than or equal to 8. So that goes to 0. We have just done that, right? You remember that? Hello? Do you want me to show that again? So now we are going for two dimensionals. In two dimensions, what is the volume of sphere? Volume of sphere is this one. So constant into r to the power of n. Now we have d dimensions, so n becomes t by 2 to the power of d, right? We do have d dimensions, so this becomes 2 to the power of d. So the whole equation becomes kd r to the power of d by 2 to the power of d. When r is equal to 1 for our sphere, as it is a unit hypersphere, so this becomes kd by 2 to the power of d. So when we apply d tends to infinity, kd by 2 to the power of d. Okay, kd by 2 to the power of d. And we just derived what will be the value of kd when d tends to infinity. So if you want me to derive that again, I'll do that. But we have just recently done that. You want me to do that again? How is that? So I can just derive that again for you. So you will not get confused. So I'm trying to find out what is the value of kd when d is infinity. What is kd here? D to the power of infinity. Kd is nothing but that constant. The constant is here. It's pi to the power of n by 2. That becomes d by 2 by gamma of d by 2 plus 1, right? So I'll say gamma as d as even now. It doesn't matter when d tends to infinity whether it is even or not. It doesn't really matter because 10 lakhs plus 1 doesn't really matter. 10 lakhs is even, plus 1 rupee is, it makes it odd. So that one dimension will not give us a big impact. So that is, even d is just not like 10 lakhs. It can be much bigger than that. Infinity is very, very bigger. So now I'll assume that d by 2 by, d by 2 is nothing but what we say, it's d by 2 factorial. Okay, so d by 2 factorial. Now this becomes limit pi to the power of 2 by 2, and this can be approximated as there is a Stirling's approximation I just have shown you. So this is Stirling's approximation. How can we approximate n factorial when n is too large? 2 to the power of pi, I mean root over 2 pi n into n by e whole to the power of n. So now n should be replaced with d by 2. So that becomes 2 pi n into n by e whole to the power of n. That is what it is given, right? Now n has to be replaced with d by 2. So pi to the power of d by 2 by 2 pi d by 2 root of into n is d by 2e and the n is d by 2. So 2 will get cancelled. So that becomes pi to the power of d by 2 by root of pi d into d by 2e whole to the power of d by 2. So I'm just, as these powers are equal, I can rewrite this as 2 pi e by d whole to the power of d by 2 into 1 by the root of pi d. Okay. So now I'm applying limit d tends to infinity. And we know 2 pi e is less than 18. It's coming somewhere around 0.7.0. So this is 18 by d whole to the power of d by 2. And d is very large. Let's take d as 10,000, right? When you take d as 10,000, what does this becomes? It becomes 0.00018. So when this 10 grows on increasing, it is approaching close to 0, right? So now this is approaching close to 0. So this is 0. 0 multiplied by anything is will become 0. So that is why KD is becoming 0, right? Now if I go back here, when D tends to infinity, KD is becoming 0. So the whole thing is becoming 0. So what does that means? What does that means? All the volume is in the corners, right? That is what it actually means is. So now, initially what we have found out, 52% of volume is occupied by this sphere. Now the volume occupied by this sphere, this whole area is 0. That means all the volume is here in these edges. Okay. If I represent those edges with something like this is my 3D. If I say I have 3D, I have some spikes like this, two corners at this edge, two corners, something like this edge, two corners at this edge. Okay. On four sides, you will have four corners you will see. Like if this is my floor, if I put something like this, so I'm just dividing this. So this is one spike, then this is one spike. So at every corner, we'll have two spikes. So for 2D, you will have four. For 3D, how many will be there? Eight will be there. Four on the top, like if you take 3D and if you inscribe a sphere like this, you will have one space here and you will have four corners here. So eight corners will be there. So for 3D, you will have eight corners, something like this. So what this says in 2D, this sphere is occupying 78.5 percentage and these spikes are occupying remaining 22 percentage. When it comes to 3D, sphere has 52 percentage. These corners will occupy 50 percentage. When it comes to d-dimensional, the sphere is not occupying any space, 0 percentage of space. 0 percentage of volume is occupied by the sphere. All the volume is inscribed in these corners only in higher dimensional space. That is what in d-dimensional, volume of sphere by volume of cube is equal to 0 means volume occupied by sphere is equal to 0. So if volume occupied by sphere is equal to 0 means where all the volume is? All the volume is in the corners only. Okay. So that is what this particular proof will tell us. This proof tells us in higher dimensions all the points are in the corner. The reason being all the points will be in the I mean we don't have any volume in the middle, right? The volume in the middle of this cube is 0. We when we have 0 volume here, the only available space is these corners. Okay. So the only available space is those corners. So what does that actually mean? Sorry, I realized. So now we derived lot of stuff. What that lot of stuff is saying is that in higher dimensions, we don't have any volume occupied by sphere, right? We have a sphere kept inside this big cube in t-dimensional space, and the volume occupied by this sphere is 0. When volume occupied by this sphere is 0, where all the volume is residing, where 100% of the volume is residing, 100% of volume is residing only in the corners. Okay, only in these corners you have the 100% of volume in the higher dimensions. If 100% of volume is in the corners, then if you have one point where that point actually lies, that point lies in the space where there is a volume, right? Volume means there should be a space for that point to exist. So where there is space, the space is at the corner. So if there is any point, that point always lies in the corners in higher dimensions. It will not stay in the middle of the space. It always stays at the corners in the higher dimension space. Let's suppose if you have like a point like something like this. so on D, some bigger dimensional point, it always, if you take any point in the higher dimensional space, it always lies close to the corners, is what this property actually says. It cannot stay in the middle or somewhere like this. It always stays in the corners. Okay, so that is one important observation. The two observations that we made is volume of a sphere in higher dimensions is 0. Is that the first one? Where is that? Volume of hypersphere goes to 0 in higher dimensions. And now the second property is the volume of sphere inscribed inside a hypercube or a cube in higher dimensions is 0. We know volume of a sphere in higher dimensions is 0. So when you inscribe this inside a square, so the volume here will goes to 0. So the volume is 0. So the volume, all the 100% volume resides in these corners. So if you have one point, and that point will always reside in the corner, because where there is a volume, there only we can have a point. So that is one important observation. All in higher dimensions, all points are in the corner. Okay. So all these will conclude to one thing, which is like in higher dimensions, the analysis of any data is really a big problem. Why it is a big problem is what we will understood with further conclusions that we made. For now, we made two conclusions. The first conclusion is volume of hypersphere in higher dimensions is 0, and the second conclusion is all the points in higher dimensions will reside only in the corners of a cube, right? So that is one thing. The third important property that you have to really understood is this property. Okay, so we made two assumptions. Now we are going to make the third assumption, which is also very interesting. So we will come forward understanding that. Now this is the diagram that we do have. Okay, so we are just trying to come down to 3 points. So this is the first important point that we made. Volume of hypersphere goes to 0. And the second point is in higher dimensions, all the points are in corners. And we are coming down to third point derivation, which is this third point. Points are not just on the corners, they are on the boundaries. They are on the boundaries. Okay. So look at the way the points are shrinking in higher dimensions. They all are getting converged to the surface, the corners of that particular surface. So I'll just prove that for you now. With that, you will understand how the data looks in higher dimensional spaces. Okay. So now it's just something like this. From where we are coming, like this is a 2D space. The points are something like this. A point can stay at any place. If this is a 2D space, the point can stay at any place, right? It can spread along all the space. And now in higher dimensional spaces, what we are saying, if you have a hypercube, treat this as a hypercube, the points can lie only in the corners is what we derived here. It cannot stay anywhere beyond these corners. That is what we actually derived. So all this space is void. All this space is void. If no points can exist in this space. Now the third conclusion is what we are coming down to is this one. So look at this diagram again, and let's just understand what is the volume that is inscribed in this space. In this space, we are just interested in the amount of volume that is present in this small edge. Okay, so I am taking two spheres. The outer sphere is of radius r, and the inner sphere is of radius r minus e. That means what is this? What is the length of this? The length of this is e, right? This is r. This is r minus e. So this is e. So the length of this particular piece is e. Okay. So now to find out the volume inscribed within this space, within this orange space, what I have to do? I have to find out the area. So to find out the volume inscribed this, what I have to do? Volume of r minus volume of r minus e circle. So if I subtract this volume from this entire volume, I'll get this volume. It's something like this. If you take the square, if I want to find out this particular volume, what I have to do? I have to find out the whole area and I have to find out the volume of this square and then subtract it so that I'll get the volume occupied within this space, right? I hope you understand that. So I have one square like this. Let's say the side is 2, 2, and I have another square inside that, which is something like this. I have one more square inside this, which is 1 and 1. Okay. So the volume of this is 1, volume of this is 4. The outer square is 4. So the volume occupied by this space is 4 minus 1, right? So the volume occupied by this is 4 minus 1, which is 3. So volume inside here is 1 and volume here is 3. The same way you're actually trying to do for these spheres. Let's see what happens when we do that for these spheres. Okay. And this comes down to one assumption, I mean, one derivation. So that will conclude most of the stuff that we want to study in the higher dimensions, and we can prove how the points actually looks like in higher dimensions, which would be very interesting. Now we want to calculate what we are trying to calculate. What is the volume occupied by this particular circle line? This particular line is what we are interested in. So for that, what we have done, volume of the outer circle minus volume of the inner circle by volume of the outer circle. Because we know, right? We already have done this. If the whole circle is having 100% of volume, what is the volume of this particular area? So that becomes into 100 by V of R. Right? I already have shown you before. Now I just apply the formula for these things. Okay, volume of the sphere. What is the volume of sphere in d-dimensional space? Kd, I'm taking a constant Kd, R to the power of d, right? Again, I'll go back there to show you. So this is what we have. And when it comes down to this formula. I'll call this as constant Kd all the times. And this is R to the power of n. N is the number of dimensions, so n becomes d. So I call this as Kd R to the power of d minus Kd R minus E whole to the power of d by Kd R to the power of d. Okay. Now Kd gets cancelled. Okay, all the Kd's will get cancelled because I take Kd common from the upper space, Kd common from the below space, and cancel Kd's. And now I'll be left with R to the power of d minus R minus E whole to the power of d by R to the power of d. Okay. Now I'll take the Rd common from the upper from the numerator. So this becomes 1 minus E by R whole to the power of d by Rd. Okay. So I'm going to cancel Rd. So it all comes down to this limit d tends to infinity 1 minus E by R whole to the power of d. Okay. So you know this, right? Now, what is this? You know, E is very, very small when compared to R, right? E is very, very, very small when compared to R, right?
Yes.
So when E is very, very less than R, so this goes to 0, right?
Yeah. We don't want to be zero.
E by R goes to 0. Let's take this example. Let's say 1 is E, R is 10 lakhs. So this becomes 0.0000001. So this whole thing will goes to less than 1. Less than 1 instance, it's almost goes to 0, right? I mean, it's almost goes to 1.
No first. Yes.
No, no, no.
There's
This,
one minus zero, right? So
no, no. Just take this as an example. 1 minus what does this become? Let's 0.0000, something like 1. So this would be less than 1. That means it would be somewhere like 0.9,
Something, yes.
something like this. So just apply infinite for this. What happens? Just take a simple example. If I multiply 0.1 square or 0.9 square, what is this becoming? 0.81. 0.9 cube. What is the value of this? 0.9 whole cube. 0.9 into 0.9 into 0.9.
Greater than 1.
0.
0.7.
0.0729.
Okay. Now if you go to 0.9 whole to the power of 10, what is this happening? It's coming to 0.3, right? So even if it is if it is 0.99999, when it goes to infinity, it approaches to 0, right? Agreed?
Yes.
So when this is less than 1, this whole thing is approaching to 0. So the whole value is coming down to 1. What does this mean? So this means 100% of volume is residing in this small edge, I would say surface. Okay. So when you take any diagram, this small space, the surface is occupying 100% of volume. That means all the points are not only in the corners, but are in the boundaries on the surface. Whether you can take the square as well. Even if you take the square and if you subtract a square in higher dimensions, all the 100% volume will be residing in this small edge or on the surface of that particular outer square. So that is the third assumption. Points are not on the corners, they are on the boundaries, mostly on the surface. Now, just look at how we are approaching to this point. It is as simple as this. We are approaching to this in this way. So we started from this. So this is the conclusion which you have to understand. With all these derivations, we came down to 2 points. The first finding we have found is volume of sphere is 0 in higher dimensions. When d tends to infinity, it is going to 0. Volume of sphere in higher dimensions is coming to be 0. And with the second findings, what we found is all the points will reside in the corners. Only in the corners you'll get all the points. And the third finding says that not only the corners, the points will just stay in that surface, the minimal surface that we do have on the, it's very, very less when compared to the length of it. You can almost say this line. Okay, all the points in higher dimensions will stay here. Okay, so with this in place, what you can understand is to find the similarity, we started with 2 points, right? We found out the similarity by calculating the Euclidean distance or cos theta, right? So when 2 points are close to each other, you cannot actually distinguish both the points, even though they come from different classes. Let's suppose I have 1 point coming as cat class in higher dimensions and 1 point coming as dog. They both look as the same because they are very close to each other in higher dimensions. So you cannot actually distinguish between a dog and a cat. Even though they are different points altogether, they do they to every vector. I mean, every point that you take in a vector, when you say point, you already know each row can be represented as a vector, and each represents one particular feature. Like it has a specific feature and it has one label that determines whether it's cat or dog. So all this future vector of cat and all the future vector of dog is coming very close, almost on the surface. Both the points are residing almost close to the surface. You can represent it this way. Let's suppose all the cats are somewhere like this, and all the dogs are somewhere like this. Let's suppose all the dogs are somewhere like this. You cannot actually use the cosine similarity or you know, Euclidean distance or Mahablanese distance, because even if you take the angle, they both looks the same. The distance doesn't able to the distance will not be suffice to calculate the difference between the 2 points. The distance would be very minimal, like 0.000000 something, somewhere like 1 2. So that distance will not be sufficient to differentiate the features. I mean, differentiate or differentiate the two future vectors. Okay, so that is the conclusion of this lecture. So look at this. In higher dimensional spaces, the difference between distances shrink. So the distances will almost shrink. They almost will be very close. The one point will be very close to the other point. The dog feature vector will be very close to the cat feature vector, if you take an example. So the distances shrink because most of the volume is concentrated near the boundaries or surface. Okay, most of the volume is concentrated near the boundaries. That is what we have actually learned by doing different derivations, leading to the points that are approximately equidistant from one another. In that closed space, if you take any 2 points, they looks like of equal distance, even if it is dog, cat, whether it is any other animal, if it is rat or whatever it is, they all looks equal. So this make traditional distance metrics less useful. What are the traditional distance metrics? Euclidean distance or Mahablanese distance. They all becomes very less useful. We cannot use those distances to distinguish between the futures. And as a result, techniques that rely on distances such as clustering can become less effective without proper handling. Okay, so what does this says is, in higher dimensions, you cannot use these metrics like distances or angles between 2 points to distinguish the features. Okay, they all becomes useless in higher dimensions. So what is the solution for this? Do we need to go do the analysis on higher dimensions? Do we actually need to go ahead and do that? No, because any metrics that you do have is failing in higher dimensions. So you shouldn't do any analysis in higher dimensions. So what is the alternative? The alternative is reduce the dimensions, bring down to the reasonable number of dimensions. When you reduce the dimensions, that actually really makes sense. That really makes a good sense of actually doing that stuff. So you right now you are just talking about distances, right? I also have to show you how the angle between the points looks like in higher dimensions. That is also a very important thing that I would like to put forward for you. Where is that slide? Um, let's look at the angle in higher dimensions, okay, with just a simple example. So do you feel, I mean, when I first heard about this higher dimensional spaces, it looks very interesting for me. I don't know how you actually felt about this, but this is an very interesting conclusions made in higher dimensions. Till now I was talking about the volume and the concentration of points, and when the points are such a close, when the points are residing in such a close space, it doesn't, the distance really doesn't matter. Distance between any 2 points doesn't really makes any sense. Now I want to prove you how does angle also doesn't make any sense in higher dimensions. Okay, with that we will actually conclude the major things, and then we already heard about the solution. What is the solution? When you can't do anything in higher dimensions, you have to reduce the dimensions. That's the only thing. So let's suppose I have 1,000 rows. Okay, let's suppose I have 1,000 dimensions. Do I need all the 1,000 dimensions? Do all the 1,000 dimensions contributes to differentiate the future? Let's suppose I have legs. Cat will have 4 legs. Most of the animals will have 4 legs. So do you think this is an important feature to distinguish between two animals? Count of legs. Yes or no?
No.
So you can just eliminate this dimension so that you are reducing the dimensions of you're reducing the dimensionality. So let's suppose you reduce one dimension with this. In such a way, you can have n number of dimensions to reduce. Let's say born country of that species. Does this contribute to the to distinguish those two creatures like cat and animal? Cat and the dog. Does born state helps to decide distinguish between cat and dog? No, right? So we can get rid of all these useless dimensions, and you can you can restrict only to the dimensions that are giving you the useful information. Okay. So it all comes down to which dimensions has the useful information and which doesn't has the useful information. I can also give you a good example. Let's suppose I'm trying to find out something about the human, mankind or whatever it is. So for that, I have this particular data. Okay. I have this data, which is like I have the height and weight. Height and weight. If I want to understand what is the growth rate of humans in a particular country, the height I would say 4 feet and the weight is 30. The height is 5 feet. Sorry. Uh, right, sir. Let's say the height is 5 feet and the weight is 35. Okay. And the height is 5 feet and the weight is 35. The height is 6 feet, the weight is 40. Height is 7 feet, the height is 45. Okay. So just look at this and what do you understand? Do you need both the variables? You have to look at it this way in the point dimensions. Okay. So height is increasing and weight is increasing. They do have positive covariance or negative covariance, or you can put it like positive correlation or negative correlation.
Negative.
Who is that?
It's positive actually based on x-axis, y-axis is depending on x-axis, right? So it is a positive one.
Yeah. So if one variable is increasing, the other variable is also increasing. So it has a positive covariance. It has an positive correlation between the points. Okay. So they all will look somewhere like this. Okay. So if if I reduce this dimension, what happens? If I get rid of this, the still points, the variance will be preserved, right? The data is preserved because they are in terms of scaling they are different, but in terms of dimensionality they have the same information, right? As they have a positive covariance, the relation between them is very similar. We can get rid of one of them because that information is also being carried by this dimension, right? Because look at this, these two are similar. When one is increasing, the other one is also increasing. That means they have similar relationship between them. When they have similar relationship, you can get rid of one parameter out of it, right? You can take the height and weight of the cat and dog as well. Dog's height will be more and weight will be more. Cat's height will be less and weight will be less. Do you need both height and weight of the cat to distinguish between both the animals? You just need height or weight, right? If you take one, because they are both interrelated, height and weight are interrelated. They both have high correlation between those. I mean, those two random variables have high correlation. So when two variables have and two dimensions has very high correlation, uh, I mean, using both the dimensions will increase the dimensionality, but it will not give you any additional information. That is what you have to understand. So you are not getting any additional information out of these two dimensions. Even if you have one dimension, you can get that, you know, you can get the weight value because they are directly related. They have positive correlation. That means when the height is increasing, weight is also increasing. So when you have that relationship between those two dimensions, you can get rid of other dimensions. But you have something like if we have 9 and 30, now the correlation is changing. They don't have any correlation or covariance between them. The covariance between them is not there. When you don't have a covariance, you have to consider both the dimensions. When you see the data has high covariance between those two, you can get rid of one of the dimensions. You understand that? Let's suppose when they have high covariance, when I have new height, I can guess the weight as well, right? When they have a new height, when I can guess the new weight. So there is no point of injecting both the dimensions. You can go with one dimension. When there is no correlation, then you have to inject both the dimensions because they both have important information. Agreed with that? Hello? Okay. I'll talk about this. I think this may not be right time, but I'll talk about this later. But let's conclude this. How the angle between the dimensions look like in higher dimensions. So let me take an example of a square. And these are the main axes of the square, right? And these are the diagonal axes of the square. Now, can you tell me what is the angle between this point and let me also mark the points. This is origin, which is 0, 0. This is origin, which is 0, 0. And I would say length of this is 1, 2. Let's take this as two-dimensional cube. So this becomes square. This becomes 1, comma 0, right? This becomes 1, comma 1, right? So this is 1, comma 1, and this is 1, comma 0. Now, if I have to find out the angle between these two, what can I do? I can apply cos theta, right? Cos theta is equal to 1 comma dot product of this and this, vector A and vector B. So that becomes 1 into 1 plus 1 into 0. That becomes 1 by mod A, which is root 2 into mod B, which is root 1. So that is 1 by root 2, which is equal to, now theta is equal to 45 degrees, right? Right?
Yes.
At two-dimensional space, in two-dimensional space, it is 1 by root 2. Now let's take three-dimensional space, which is cube, and find out the angle between any two points, the diagonal axis and the main axis. So then one of the points will be 1, 1, 1, and the other point is 1, comma 0, comma 0. Is that right? I don't think. Yes. So these are the 2 points. I'm just extending the other dimension between the 2 points.
Mm.
Okay. So just if you want to look at the floor part, where does 1, comma 0, comma 0 lies? Just on the x-axis, right? So if you take this as a floor, okay, and the center of the floor as point 0, comma 0, comma 0. So on x-axis, it becomes 1, comma 0, comma 0. Okay. So the room, we are in the middle of the room. And this is the door here. Let's suppose this is the door. And there is one part here. This is one part here. So the x-axis and y-axis stretches like this. This is 1 and this is -1 of x. This is -1 of y. This is +1 of y. Understood now? So this is 1, comma 1, comma 0. Now we are going through the walls. These are walls, okay? On the walls, the diagonal, how does the diagonal actually comes? How does the diagonal crosses? From the top edge of this corner to the bottom edge of the other corner. right? Just imagine this. This is the wall. On the top edge to the bottom edge will be the diagonal axis. Okay, that touches the horizon. Will that touch the horizon? If you take the basis, it will not. Look at this in the other way. Look at this in the other way. So this is 0.0, and this becomes on this axis, which is Z. Okay, so this point will become 0, 0, 1. Let me show you a simple diagram on internet that we see. I just want to look at the diagonal axis. Cube with vertices. Vertices and diagonal axis. Okay. A cube with body diagonal axis. Just try to understand the angle between any 2 points, diagonal axis and the horizontal axis. What is this? Here is the example. Okay, now take this example now. It's right there. Okay, we have this now. And now for 2 dimensions, we know which is 2 root 2 comma 1. Now, what is the diagonal element here? 1 comma 1 is something which is there. And now, we know the angle between these two is 90 degrees, right? So this is 0, 0, 0. This is 1 point. This is 1, 1, 1. Okay. So also I want to show you how are the diagonal axes look like. Okay. So this is the diagonal axis. Here is 0, 0, 0. And now we want to find out the angle between the diagonal axis and the main axis. Okay, so let's actually try to find out that and see how does that actually comes down to. So here what we have found, this is the main axis, right? So this is the main axis, and we have found out the angle between the main axis and the sub-axis. Point options. So this is one of the point. This is the main axis, and from the main axis to the diagonal axis, we have found out an angle between them. So here, what is the main axis? This is the main axis, and this is the main axis. This is Z axis. To the main axis to the diagonal axis is what we have to find out. So what is the point between these two? This is the diagonal axis, right? This is diagonal 0 to 1, 1, 1. And this is the main axis 0, 1, comma 0. So can I find out the angle between 1, 1, 1, 0, 1 and 0? So this diagonal and this main axis. This is main axis. Are you getting me? I don't know. So I'm saying, like, I'm trying to find out here what I have done. I have tried to find out the angle between the main axis. This is x-axis for the square, this is y-axis for the square, and this is the diagonal axis. I tried finding the angle between diagonal and the main axis. Here also I'm trying to find out the angle between diagonal axis. which is from 0, 0 to 1, comma 1. One border of this room to the other border of the room. And also the second one is this original axis. Original axis is this one. Right? This is the original axis. So these two vectors are 1, comma 1, comma 1, 0, comma 1, comma 0. If I found out cos theta between these two, what I'll get 1, comma 0 is 0, 1, comma 1 is 1, 1, comma 0 is 0, 1 by root 3, 1 square plus 1 square plus 1 square into 1. So for 3 dimensions, I got cos theta as 1 by root 3. Okay. For 2 dimensions, we got 1 by root 2. For 3 dimensions, we got 1 by root 3. For d dimensions, I would say it is 1 by root d for d dimensions. Okay. Now let's apply limit d tends to infinity. Limit d tends to infinite. What does this cos theta becomes? Cos theta becomes 0. When t is 2 hues, 1 by 1 lakh, it comes to 0 0.00001 1 lakh times 1. So it is approaching close to 0. Right? So cos theta at some point approaching 0, not exactly 0, but approaching to 0. That means theta is equal to 90 degrees. So in higher dimensions, the angle between the diagonal axis and the main axis is 90 degrees. So we all know the angle between the dimensions, the major axis is always 90, but the interesting thing is the angle between the diagonal axis and also the main axis is also 90 degrees. What does that says is in higher dimensions, the angle between any two axes is 90 degrees. Okay. So when angle between every axis is equal to 90 degrees, can we use cosine similarity between any 2 points? Because everything goes to 0 and everything looks like same. We don't see any similarity between any 2 points because we can have many number of axes, right? And the angle between every axis is just 90 degrees. And it doesn't really make any sense to actually do an analysis on that particular part in higher dimensions. The reason I'll say why. You can take a simple example. Okay, I don't want to erase this, but let me just take you a simple example to show you why does that really makes any sense in higher dimensions when you have um, uh, higher dimensions. Point options very sorry. Sorry about that. Right here. So this is an interesting thing also. The other finding that we have done right now is the angle between any two axes in higher dimensions is 90 degrees. So now let me take this example and tell you what really happens now. Why the angle between 90 degrees is big is a very bigger problem. Okay, so the reason is here. So I'll take the 2 dimensions points. I have taken x-axis and y-axis. Okay, now what I have done is I have taken this point, any point on this y-axis. Okay, so I can take any point on this y-axis. This is 0.1, this is 0.2, and this is 0.5, or this can be 0.0 minus 2, this can be 0.5. When these are projected to the other axis, okay, we shortly will know why do we do projections and all. But understand that if I bring this point, if I bring this point to x-axis, if I want to bring this point back to x-axis, or this point to x-axis, this point to x-axis, this point to x-axis, any point to x-axis, they all falling to 0.00. So when these points are brought down to its perpendicular axis, okay, which is at 90 degrees, these points are losing their information. When they are in their actual dimension, what is happening? They have some meaningful information with them. But when we project them to the lower dimensions, what is happening? They all are losing their information and they are all residing to 0. So when two dimensions are at 90 degrees to each other, projections are also losing their information. Projections also don't have when we project to the to the other dimension, which is 90 degrees to it, there is no difference between these points. This point when projected to here and this point when projected to x-axis, they both will come to 0.0. So they don't have any difference actually. So that is one of the reasons why in higher dimensions that actually looks zero. But every axis is at 90 degrees with each other, whether it is diagonal axis, main axis, or whatever axis. Every angle is at 90 degrees with each other. When if a point is there on the diagonal axis, and if you want to move that point to other dimension, what happens is they're simply losing their information. Okay, so why they lose their information? Because any point that is on the diagonal axis when projected to the other axis, it always drops to 0 comma 0. So you are losing some information over there. So that is all where it comes down to. Even 90 degrees between the angles, every axis, it is nearly impossible, but I wouldn't say it is 90 degrees, but close to 90 degrees. When the dimensions are increasing, the angle between the diagonal axis and the main axis is approaching to 90 degrees, is coming close to 90 degrees. This doesn't necessarily needs to be zero all the times. When it can be 0.0000, some minute value. So even that is a minute value, it is close to 90 degrees, right? When it is coming close to zero, we are coming close to 90 degrees. When it is not zero, we are somewhere around 89.9.9.9.9 or something, somewhere close to 90 degrees. So all the angles in the higher dimensions, all the diagonal element axes in the higher dimensions will be close to 90 degrees. The other view for this is, look at this. So when every point, let's say this is one point, this is one point, and the both are almost 90 degrees to each other. In higher dimension space, I am taking 2 points. So there can be huge number of original axes, right? There can be, you can also put it this way. In higher dimensions, there can be very huge number of axes and also orthogonal axes. When you say 10 lakh dimensions, we have 10 lakh dimensions and also the relevant number of orthogonal axes as well. Orthogonal axes are 2 into 2 minus 1 axes will be there. 2 to the power of d minus 1. For d dimensions, you will have 2 to the power of d minus 1 orthogonal axes. Okay. I mean, we will basically we will have many number of dimensions is what I'm trying to convey. So any point can come very close to one of the dimensions, and other point will be some close to other dimension. So when you take the angle between both of them, even though they are similar, they look apart, right? Because angle between them is 90 degrees, close to 90 degrees. So that is one of the points about higher dimensions. In higher dimensions, the angle between any two axes is coming close to 90 degrees. So that parameter, the cosine similarity, also cannot be used to differentiate the points. So with all this in place, the only thing that we are coming down to is this point. What is that point? This is what we are all coming down to. That is this one. So in higher dimensional spaces, the difference between the distances shrink, and we already have seen that. And what is the other point? Because the most of the volume is concentrated in the borders of surface, leading to points that are approximately equidistant from one another. This makes traditional distance metrics less useful, and as a result, techniques that rely on distances such as clustering can become less effective. Thank God, less effective without proper handling, dimensionality, reduction, or using alternative distance metrics. So with this in place, we know analysis in higher dimensions is very difficult, and we found out 4 points. The one is the volume of sphere in higher dimensions is 0. The second thing is most of the volume is at the corners of the cube. The third is most of the volume will reside in on the surface. Surface is like that small e is what it is saying. Points are not just on the corners, they are on the boundaries on the surface area. And the fourth one is in higher dimensions, the angle between any two axes is 90 degrees. That makes cosine similarity also useless. Okay. With that in place, what you have understood, you understood analysis in higher dimensions is really very difficult. I have to explain normal distribution as well. in higher dimensions. You remember what is a normal distribution? Normal distribution. Anyone? Normal distribution, standard normal distribution, standardization, Z-score.
A normal distribution mean is 0 and standard deviation is 1.
Standard normal distribution, mean is equal to 0 and standard deviation is equal to 1. That's right. How does the normal distribution graph looks like? Can someone say me the example?
Mean is in center and it's looks like bell shaped.
Right, exactly. That's good. So it's like a bell-shaped curve. Most of the points will lie beside the normal distribution. I mean, around the mean. Can someone say me what is that rule we have with normal distribution 68, 95, 99.7? 68, 99.5, 97. Okay. Keep revising that. I don't have anything much to say beyond that. But I'll just cover these slides so that we will not get lagged so much. I want to complete this by end of next week. So I just go ahead and take 30 more minutes to complete this stuff. It is easy. Now you might have understood why we need dimensional detection, right? We understood high dimensionality problems. Okay. So we call that as curse of dimensionality. We call that as we saw the problems in higher dimension. So I call that as curse of dimension. What is dimensional detection? The process itself, the name itself says the process used in data analysis to reduce the number of variables in the data set while retaining as much information as possible. So we are retaining the information, but we are reducing the dimensions. How to retain, what are the methods to say, like we are retaining the information, how much information we are retaining? We will see all that stuff in the coming things. But you have to understand what is dimensional reduction. Dimensional reduction is nothing but you are reducing the number of dimensions, but you are retaining the information within it. As I told you, when height and weight are carrying the same information, when they are highly correlated with each other and we don't have any data point which is contradicting to that particular covariance or high correlation, you can get rid of one dimension because they both are carrying the same information. So when the height is increasing, weight is also increasing. When there is a new data point, the weight will also be the same for that data point. It will not be different or less when they are highly correlated and the correlation is equal to 1. So they are positive. When they are positively correlated, when one variable increases, the other random variable also increases. So you don't need both the variables. When high covariance is there, you can get rid of one variable. Okay. Are you able to accept that statement? When there is high covariance between two variables, we don't need both the dimensions. One dimension is sufficient to carry the same information. Are you able to agree with that? If not, if yes, why you are able to agree with that? And if not, why you are not able to agree with that? I said I have two random variables. One is height and the other one is weight. When height is increasing, weight is also increasing. They both are positively correlated with each other. Okay. So now I'm saying like both height and weight are carrying the same information. So I will get rid of weight dimension to reduce my dimensionality in my data matrix. So that is what the statement I have put forward. The reason I am saying is the When I say they both carry the same information, that means when height is, let me say like this. So I have three data points like height is equal to 30, something like this. When I say three data point, I would take some set of data points like height 10, 20, 30, 40, and 50. Okay. And the weight is 20, 40, 60, 80, and 180, 50 is 100, right? Okay. So this is my height and this is my weight. I'm saying both are carrying the same information. Why both are carrying the same information? Even if I don't have this information with me, but when I know they both are highly correlated, when I get some value like 60, I can predict this value, right? When it is 70, I can predict this value. When 80, I can predict this value. So I can derive this value from the existing future. That means they both are carrying duplicate information. If I know this 180, I can get this height value, which is 90, right? So they both are carrying the same information. So we can get rid of one information. Even if we have this information, we can get this information when they both are correlated with each other. That means when one is increasing, the other should also increase. If that correlation is there, we can get rid of one dimension. We can get rid of one of this dimension, weight or height. It's your choice. You can keep one dimension and you can use that dimension for your analysis. Are you able to agree with that,
Yes, yes.
everyone?
And the other column should also be the same data, right? So if it's following 20 difference, so it should be 20 difference across the table. Otherwise, if any difference is there, then it won't agree, right? So
No, no, no. That is not something like this. For better understanding, I gave this example. But even if that is different, if one is increasing, the other will also increase. If other is also increasing, the correlation can be something like this. This is also correlation. This is also highly correlated. This is also highly correlated. This is also highly correlated. The scaling doesn't really matter. How much the y is increasing when the x is increasing is doesn't really matter. So they both all carry the same information. This is the line we are seeing where the slope is 1.
okay.
Okay. This is what we are seeing. So in this case, we are able to accept that if we don't have one variable, we can get rid of the other variable, right? In the other case, if this is also correlation, this is also correlation. These are all positive correlation lines, right?
Mhm.
So when this is agreeing and this is what you are able to accept that they are carrying the same information, because that is you are able to see the difference. See, this can be not the same difference, but some scaling factor of that, right? With it has some intercept, some different slope, but they are when we say they both are correlated, there should be some relation between the variables. This case, it is simple relationship, which is y is equal to x, slope is equal to 1 plus some intercept, right? But
Yeah.
this line will also have that relationship between x and y, the same relation, same kind of relationship, linear relationship.
Okay, thanks.
When there is a relationship, they both carry the same information. When you know one variable, you can derive the other variable. If you know the other variable, you can derive the first variable. So when there is high correlation, you can predict the other variable very easily. They both carry the same information is what that actually means is.
Okay.
Agreed. So
Yes.
I see very low responses. I don't know whether people are understanding or not.
When Pooja is in waiting room, then you accept
So
that.
let's see that. Sai, do you know how to set that accept all option? That's okay. We can see that tomorrow maybe. I'll just go with this. So that is a dimensionality reduction process. So we reduce the dimensions, and you should be able to accept that when there is high covariance, you can get rid of one of the variables or one of the dimensions. When two dimensions has high correlation, you can get rid of one of the dimensions. We just have seen one of the examples. why we actually need dimensionality reduction. The one thing that we have seen is in higher dimensions, the distance metrics are becoming useless, which we call as curse of dimensionality. So we need dimensionality reduction, right? The second thing is it is hard to visualize the higher dimensions, right? So visualization would be easy in lower dimensions. And computational efficiency, when we have high dimensions which carry duplicate data or which don't have any information within it to distinguish what we want to achieve as a target variable, which is label out of the features, you are just increasing the computational costs, right? And let's suppose if you are incorporating height and weight into your data, which is carrying same information, the computational efficiency is increasing, right? That is one of the examples. And let's not bother about overfitting, which is an uniquely different concept. Overfitting and underfitting, I would explain you when we actually go to the models. So just understand this. High dimensional data often have too much noise. Noise in the sense unnecessary data. You are putting unnecessary data into your mind so that you cannot accept any new data and you cannot able to process it, right? So make sure you have only the right set of information or right set of data given to the model. It's just like how a person will be more valuable if his mind has more valuable information. Similarly, if a person's mind is filled with lots of noise and unnecessary things, his I mean his attitude will also be the same. It's similar to that. When you feed the right data without noise to a particular model, it behaves in a very well mannered way and it gives you the right amount of efficiency as a model to predict anything. And if you feed lots of noise and unnecessary data to it, it messes up and it will not give any right information or right results as a model. Okay, that is what actually feeding noise to the model means. Feeding the noise in the sense feeding all unnecessary dimensions, all unnecessary dimensions. We have seen what are unnecessary dimensions actually means is. So what are the unnecessary dimensions? You just have seen born country of that particular feature when you are distinguishing between cat and dog. That's an unnecessary data. If you feed to it, it gets confused. That is an unnecessary for it, but it also tries to consider that particular dimension also to evaluate the label, which is unnecessary. We know which that is unnecessary, but model, when you fed that data to the model takes that data and it feels like that is also important. So it also considers that and messes up the output. Okay, so never feed unnecessary data to the noise. Make sure you are feeding the right set of data and right set of dimensions to the model. But you will gradually understand feeding the right data to the model in the upcoming things, and also what about overfitting and underfitting. But the only point here that you need to take care of is why you are doing dimensional detections is what you have to understand. The major important point that we have divided so far is this one, and you also, this is very well aware of it. This is computational efficiency, which anyways, as dimensions increase, computational efficiency also increases, the cost increases, the amount of GPUs that you need also increases. Okay, that's why we need dimensional reduction. And now you have to understand what is intrinsic dimensionality and what is extrinsic dimensionality. Okay, intrinsic dimensionality means the number of dimensions needed to describe without losing important information. So out of 100 dimensions, only 2 to 3 dimensions will have the important information that is needed to derive the label by the model. What is label? Label is output derived by the model when you fed the features to that model. So those dimensions are called as intrinsic dimensions. The dimensions which carries useful information are called as intrinsic dimensions. Okay, without losing information. Okay, so those dimensions are called as intrinsic dimensions. So the intrinsic dimensions and extrinsic dimensions. Extrinsic dimension means all the dimensionality. It will include all the dimensionality. Okay, so if you have 100 dimensions, out of 100 dimensions, you just have valuable information in 2 to 3 dimensions. And total you have 100 dimensions. These 100 dimensions are called as extrinsic dimensions, and these intrinsic dimensions are called as, I mean, these 2 to 3 dimensions are called as intrinsic dimensions. When you say intrinsic dimension, that dimension has all the data, or all the information that is required to predict something. Okay, and you know what is the difference between data and an information? That is what we started this discussion with, right? Information is the valuable information that we can retrieve from the data. So that valuable information to derive anything will be residing in these 2 to 3 dimensions. So you have to find out these 2 to 3 dimensions. So the next thing that you are going to learn is how to find out these 2 to 3 dimensions in this 100 dimensions is what you're going to learn. You cannot simply go and choose randomly, right? Out of these 100, you cannot go to every column and see, okay, this column has important information, this column has important information. If you do that manually, it takes ages. Okay, so the next thing that we're going to learn starting tomorrow is how to predict these 2 to 3 columns out of these 100 columns is what you're going to learn. So that is what principal component analysis, singular value decomposition, linear discriminant analysis, these 3 models that you're going to learn, these 3 concepts that you're going to learn will help you find out these 2 to 3 columns out of the 100 columns that you do have. Okay, so that is the difference between intrinsic dimensionality and extrinsic dimensionality. And now you have to understand what is dimensionality reduction. Okay, so dimensionality reduction is what you already have seen. Now you have to understand what are the types of dimensionality reductions. Okay, there are 2 types of dimensionality reductions. One is feature selection. Okay, uh, I don't want to mess up. I think I should be able to stop for today. This is something which is important, so I don't want to continue today. I'll just stop here for today. And before leaving, what I want from you